Hi, welcome to the lesson on object-oriented programming. You're about to do something that I bet many data scientists have never done before: build a Python package from scratch. Have you ever thought about how the scikit-learn, pandas, and scipy packages actually work? I mean, underneath the hood. Like, what exactly does it mean when your code says import pandas as PD and then pd.read_CSV? You might not have known it, but you were using object-oriented programming. In fact, all of these packages are built using object-oriented programming. You'll find that object-oriented programming allows you to create large, complex, modular programs like the scikit-learn package. This lesson has two parts. First, you'll familiarize yourself with object-oriented programming syntax. Then you'll build a Python package for analyzing probability distributions. By the end of the lesson, you'll have a Python package that you can use as part of your professional portfolio. You'll also gain insight into how Python packages actually work. Let's get started with object-oriented programming.
Welcome to part 1 of software engineering practices. Here, we will go over a few techniques that we can adopt as data scientists to be better developers and prepare for production-level code. You will learn how to write clean and modular code, improve your code's efficiency, document effectively, and use version control. These are all essential skills to develop as a programmer and will really help you when implementing production solutions. In addition, data scientists often work side by side with software engineers, and it's important you work well together. This means being familiar with standard practices and being able to collaborate effectively with others on code. Let's walk through each of these practices and learn how they are applied as a data scientist. Welcome to part 2 of software engineering practices. In the last lesson, you learned how to write good code that's clean, modular, efficient, well-documented, and version controlled. Here, we will go a step further and add robustness to your code with testing, logging, and code reviews. These practices help you ensure reliability and easier maintenance of your code, which is crucial in industry.
Welcome to Introduction to Machine Learning lesson. I'm excited to be your instructor for this section. Machine learning is creating rapid and exciting changes across all levels of society. It's the engine behind the recent advancement in autonomous vehicles. It allows for more accurate and rapid translation of text into hundreds of languages. And it powers the AI assistants you might find in your home. We can also use machine learning to do things like improving worker safety and speeding up drug discovery. Machine learning is a complex subject area. Our goal in this lesson is to introduce you to some of the most common terms and ideas used in machine learning. I will then walk you through the different steps involved in machine learning and finish with a series of examples which use machine learning to solve real-world situations. There are a lot to cover. Let's get started. Welcome to the third lesson of the AWS Machine Learning Foundation course. Now that you have learned some fundamentals of machine learning, you can now start using that knowledge with AWS AI Devices. But before you get hands-on with machine learning, I want to walk you through some of the machine learning offerings by AWS. At AWS, our mission is to put machine learning in the hands of all organizations, every developer, data scientists, and researchers. We want to simplify your education in machine learning, and we want to make it easy for all developers to easily build intelligent applications. This is why in 2020 alone, we launched 250 new features and services. In just a moment, I will dive deep into the key machine learning capabilities of AWS. But before I do, I just want to set the context about the state of machine learning today. ML is critical to building modern businesses. It went from being an aspirational technology to mainstream extremely fast. Businesses are investing more in machine learning. IDC predicts AI spending will reach $98 billion by 2022, 2.5 times more than 2019. ML projects are moving rapidly from piloting to production. Gartner predicts 75% of the companies will shift from piloting to production by 2024. ML is handling real-world tasks thanks to GPUs, explosion of data, research to find new algorithms, open sourcing tools, and the cloud. ML is also getting integrated into mainstream IT DevOps processes. I hope this data motivates you even more to advance your knowledge in machine learning. Now let's learn more about machine learning on AWS.
Welcome to Udacity. My name is Sebastian Thwan. I'm the founder of Udacity, and I'm so pleased you've chosen to work with us. Our mission at Udacity is to power your career to the world's best tech education. Tech is transforming the world from artificial intelligence to cloud to mobile. If you're curious about it and you want to power your own career and get better and better, we are the team that's on your side every day, every night to make you successful. So welcome to Udacity, and I can't wait to see where this journey will take you.
The first practice we'll talk about is writing code in a way that is clean and modular. Data scientists often struggle with this when they first start coding, or even if they've been coding for years in a more research or academic setting. When you're working in industry, your code could potentially be used in production. Production code just means code that is run on production servers. For example, when you're on your laptop using software products like Udacity, Google, or Amazon, the code that's running the service you're using is production code. And ideally, code that's being used in production should meet a number of criteria to ensure reliability and efficiency before it becomes public. For one, the code needs to be clean. Code is clean when it's readable, simple, and concise. Here's an example in plain English of a sentence that is not clean. One could observe that your shirt has been sullied due to the orange color of your shirt that appears to be similar to the color of a certain kind of juice. This sentence is terribly redundant and convoluted. Just reading this makes me frustrated. This can be rewritten as, "It looks like you spilled orange juice on your shirt," and accomplish the same thing. But this sentence is much more concise and clear. Writing clean code is very important in an industry setting, where you're on a team that's constantly iterating over its work. This makes it much easier for yourself and others to understand and reuse your code. In addition to being clean, your code should be modular, meaning your program is logically broken up into functions and modules. In programming, a module is just a file. Similarly to how you can encapsulate code in a function and reuse it by calling the function in different places, you can encapsulate code within a module or file and reuse it by importing it in other files. We will see examples of this later. To get a better understanding of what modular code is, try to think of it as putting your clothes away. Sure, you could just put all of your clothes in a single drawer, but it wouldn't be very easy to find anything. And maybe because you can't ever find anything, you have multiple versions of the same shirt or socks because you repurchased them when you couldn't find them. It would be much better if instead you had a drawer for t-shirts, another one for dress shirts, another for socks, and so on. With this design, if you need a nice outfit for an interview, You don't need to worry about buying one just because you couldn't find the right clothes. And if you need to tell someone else how to find the right shirt, pants, and pair of socks, it will be much easier with this design. The same is true in writing modular code. Splitting your code into logical functions and modules allows you to quickly find relevant pieces of code. You can often generalize these pieces of code to be reused in different places to prevent yourself from writing extra unnecessary lines of code. Abstracting out these details into these functions and modules can really help in improving the readability of your code. Again, programming in a way that makes it easier for a team to understand and iterate on is crucial for production. In this lesson, you will get practice writing code that is clean and modular to help you accomplish this. Before you can deploy your code, it will need to be tested. Writing tests is standard practice in software engineering. However, testing is often a practice many data scientists aren't familiar with when they first start in industry. In fact, sometimes the insights data scientists come up with, which are supposed to be used for business decisions and company products, are based on the results of untested code. This lack of testing is a common complaint from other software developers working with data scientists. Without testing, not only do you run into execution errors in code due to software issues, you can also be dictating business decisions and affect products based on faulty conclusions. Today, employers are looking for data scientists with the skills to properly prepare their code for an industry setting, which means tested code.
When you first learned to program, you were probably using a style called procedural programming. A procedural program is essentially a list of instructions that execute one after the other, starting from the top of a file and working down. Object-oriented programs, on the other hand, are built around, well, objects. You can think about objects as things that exist in the real world. Like, if you were going to build a clothing store, the store itself would be an object. The items in the store, like shirts and jeans, would also be objects. The cash register would be an object, and even a salesperson would be an object. An object-oriented program would focus on the individual characteristics of each object and what each object can do. So an object has two essential parts: characteristics and actions. For example, a few characteristics of a salesperson would include the person's name, address, phone number, and an hourly pay. In terms of what a salesperson could do, that might include selling an item or taking an item from a warehouse. As another example, a shirt's characteristics could be the color, size, style, and price. What actions could a shirt take? It might sound silly to ask a question like that, since a shirt is an inanimate object, but a shirt could, for example, change its price. As you gain experience writing object-oriented programs, keep this idea in mind. An object has characteristics and actions. Before you start coding, let's get a better sense for what an object really is.
I'm an engineer. I got my industrial engineering degree as an undergrad and pursued to become a bioengineer in grad school. I wanted to deeply understand the pain points patients were feeling. So I was going to operating rooms, I was collecting data before and after surgery. But after a while, I noticed that I don't want to just observe problems. I wanted to create solutions and solve those problems to have bigger impacts. So that was when I got introduced to the world of machine learning.
I love the opportunity to invent and build. So on a typical day, there's no shortage of customer problems. Machine learning seems like a mystery to most, but it's actually really simple to integrate into most businesses. And That's what's exciting to me, is when I see a business integrate machine learning and benefit from it in a real way.
When we were designing this course, we wanted this course to be valuable to a wide range of individuals.
You don't need a math PhD to get started with machine learning. You only need your computer, and anyone can take this course and get an intuitive sense for machine learning so they can reason about it in a rational way.
We went really fundamental and deep into what machine learning is. We introduced different types of machine learning. And what I really love about this course is that we really broke down the machine learning workflow into each of these steps.
Once you have a foundation in machine learning, once you have a hands-on experience, you'll be able to move on to the nano degree, and you'll have a much easier time with learning some of the advanced state-of-the-art concepts.
By connecting the dot between the theory and practice, I hope that I can motivate individuals to really see the potentials of machine learning, that how machine learning can be used for solving real-world problems.
So you'll get to build a trash sorter with machine learning. You'll get to create generative music where you teach your computer how to create completely new music.
There's a good chance that machine learning can be used to make your work more efficient or bring more value to your customers.
More generally, machine learning will touch every aspect of every profession. So anyone from sports stars to musicians will benefit from machine learning. Once you finish the nano degree, you'll feel really comfortable around the machine learning concepts. And when you go into the work field, people are going to look for hands-on experience. People are going to look for the fact that you've built something with machine learning before and not just take it in theory.
Solutions that I was able to create, witnessing the potentials that machine learning has kept me going.
The typical careers when people complete machine foundations is to go into a data science role or a software engineering role. And every software engineering role is going to have more data related aspects in the future because we're dealing with more and more data as time goes on. Don't stop building, keep iterating.
There is a magic in getting hands-on with machine learning. That was what helped me to really understand it.
The first things you build might not seem good, but when you look back, you have to start somewhere, and eventually you'll build really compelling things.
Let's walk through this lesson's outline. First, we will discuss what machine learning is and the common terms and components involved in machine learning projects. You might know that machine learning involves using trained models to generate predictions or detect patterns from data. But what is happening behind the scene? In this section, we break down the different steps involved in machine learning. It's always important to connect theory to practice, so we will finish this lesson by providing a real-world example of how machine learning is being used to solve problems. When it comes to AI services, the thing is you don't necessarily need to code ML solutions from scratch. AWS pre-trained AI services provide ready-made intelligence for your applications and workflows. You can just take these services and apply them for your own use cases. Starting with Health AI, Amazon has different health AI offerings, which requires no machine learning knowledge. One example of Amazon Health AI offering is Amazon Transcribe Medical, which turns medical speech to text. Conversations between healthcare providers and patients provide the foundation of patients' diagnosis and treatment. It's very important that the information is accurate. Amazon Transcribe Medical is an automatic speech recognition short-form ASR service that makes it easy for doctors to have the medical conversations turned to text, so they can save that time and spend it on taking care of patients. AWS and Amazon's industrial AI brings efficiency and cost saving to a wide range of industries. One example of industrial-specific AI offering is Amazon Monitron, with which failure of machines can be predicted through sensors and data analysis platform. This saves money and time for manufacturing entities. Amazon Lookout for Metric uses machine learning to automatically detect and diagnose anomalies in businesses and operational data, such as a sudden dip in sales revenue or customer acquisition rates. It's always good to have a system to have your back. Amazon Lex enables you to publish your voice or text bot for use on mobile devices, web apps, and chat services. Amazon Personalize is a fully managed machine learning service that goes beyond a statistic rules-based recommendation system and trains, tunes, and deploys custom machine learning models to deliver highly customized recommendations across industries such as retail and media and entertainment. Amazon Forecast helps you achieve high accuracy forecasts that can be used for forecasting product demand, resource needs, or financial performance, and many more. Amazon Fraud Detector uses machine learning and more than 20 years of fraud detection expertise from Amazon to identify potentially fraudulent activities. CodeGuru provides intelligent recommendations to improve your code quality and identify an application's most expensive lines of code. Amazon Recognition provides fast and accurate face search, allowing you to identify a person in a photo or video using your private repository of face images. Amazon Polly turns text into lifelike speech, allowing you to create applications that talk. Amazon Translate automatically extracts text, handwriting, and data from scanned documents that goes beyond simple optical character recognition or OCR. This is to identify, understand, and extract data from forms and tables. Contact Lens for Amazon Connect enables you to analyze conversations between customer and agents. This is by using speech transcription, natural language processing, and intelligent search capabilities. It performs sentiment analysis, detects issues, and enables you to automatically categorize contacts. And last but not least, using Amazon Kendra, you can stop searching through troves of unstructured data and discover the right answers to your questions when you need them.
It's pretty obvious when a software program crashes. You get an error and the program stops running. However, there are many problems that could occur in the data science process that aren't as easily detectable as a functional error that crashes your program. All of your code can seem to run smoothly with you completely unaware that certain values were being encoded incorrectly, features were being used inappropriately, or unexpected data were breaking assumptions that your statistical models are based on. These errors are more difficult to find because you have to check for the quality and accuracy of your analysis in addition to the quality of your code. Therefore, it's essential that you add proper testing to avoid unexpected surprises and have confidence in your results. In fact, testing has proven to have so many benefits that there is an entire development process based on it, called test-driven development. This is a development process where you write tests for tasks before you even write the code to implement those tasks. We'll talk more about this later. For now, we will get some practice writing tests, specifically unit tests. A unit test is a type of test that covers a unit of code, usually a single function independently from the rest of the program. First, you'll learn how to write unit tests in plain Python, and then how we can use additional tools to make them better. Finally, you'll see examples of types of tests you'll see in data science. When you first sit down to start writing code for a new idea or task, it's easy to pay little attention to writing good code and focus more on just getting it to work. so your code typically gets a little messy and repetitive at this stage of development. This is okay. It's hard to know what's the best way to write your code before it's finished. For example, it could be difficult to know exactly what functions would best modularize the steps in your code if you haven't experimented enough with your code to understand what these steps are. That's why you should always go back to do some refactoring after you've achieved a working model. Code refactoring is a term for restructuring your code to improve its internal structure without changing its external functionality. Refactoring gives you an opportunity to clean and modularize your code after you've produced code that works. In the short term, you might see this as a waste of time, since you could be moving on to the next feature. However, allocating time to refactoring your code really speeds up the time it will take you and your team to develop code in the long run. Refactoring your code consistently not only makes it much easier to come back to it later, it also allows you to reuse parts for different tasks and learn strong programming techniques along the way. The more you practice refactoring your code, the more intuitive it becomes. You'll start to find yourself writing more organized code on your first pass with less to reorganize when you go back. Let's take a look at a couple of examples and get some practice.
We're getting close to writing some code, but I first want to clarify some terms associated with object-oriented programming. I said that an object has characteristics and actions. These characteristics have a specific name. They're called attributes, and the actions are called methods. Going back to the shirt example, the color, size, style, and price would be attributes. The action of changing the price would be a method. There are two more terms I want to differentiate for you: object versus class. Here's a reminder of what I mean by object. To continue with the shirt example, an object would be a specific shirt, like a yellow shirt, size medium, short-sleeved style with a price of $15. The yellow shirt could change its price. Another object would be a different shirt, like a green, small, long-sleeve shirt that costs $20. The green shirt could change its own price as well. Do you notice anything special about the yellow shirt and green shirt? They both have the exact same attributes. In other words, they both have a color, size, style, and price. They also have the same method. It's like they came from a blueprint, a generic shirt consisting of all the attributes and methods. This generic version of an object is called a class. You've just hit on the power of object-oriented programming. You only need to define this blueprint, known as a class, one time, and then you can create specific objects from the class over and over again. In other words, you can use the shirt blueprint to make as many shirt objects as you want in any size, shape, color, style, and price. Keep this picture in your head of how the words class, object, attribute, and method relate to each other. These are fundamental terms in object-oriented programming, and I'll be using them throughout the lesson. We're going to see what all of this looks like with Python code. First, I'll give you an overview of object-oriented programming syntax. Then you can play around with my code and you'll write your own class.
To start, let's talk about the relationship between artificial intelligence, or AI, and machine learning. AI refers to the broad capability of machines to perform activities using human-like intelligence. Machine learning, or short form ML, is a type of artificial intelligence. It allows computers to automatically learn and improve from experience without being explicitly programmed to do so. Using machine learning, computers can learn from data to discover patterns and make predictions. Supervised learning is a type of machine learning technique in which every training sample from the dataset has a corresponding label or output value associated with it. As a result, the algorithm learns to predict labels or output values. You can use supervised learning to do things like predict the sale price of a house or classify objects in an image. You will learn more about supervised learning in this lesson. In unsupervised learning, there are no labels for the training data. The algorithm tries to learn the underlying patterns or distributions that govern the data. You will discover more about this technique later in this lesson. Remember, in supervised and unsupervised learning, models inspect data to discover patterns. Then humans use the patterns learned by the model to gain new understandings or make predictions. There is another type of machine learning called reinforcement learning, which takes a different approach. Reinforcement learning is learning what actions to take in a situation to maximize reward. It is similar to how you might train your pet. If your dog does something you want it to do, you might reward it with a treat. If it does something you don't want it to do, you might correct it with a small penalty, like raising your voice just a little bit. Your dog learns to do the things that get a treat and avoid doing things that get a correction. In machine learning, reinforcement learning works exactly like this. Now let's see how machine learning helps solve problems and how this differs from traditional problem solving. In traditional problem solving with software, a person analyzes a problem and engineers a solution in code to solve that problem. For many real-world examples, this process takes a lot of time. It might even be impossible. This is because a correct solution needs to consider numerous edge cases. For example, imagine the challenging task of writing a program, which can detect if a cat is present in an image or not. Traditional problem solving would require careful attention to details like varying lighting conditions, different types of cats, colors, etc. In machine learning, we have a flexible component called the model. We also have a special program called the model training algorithm to adjust the model to real-world data. The result is a trained model which can be used to predict outcomes which are not part of the dataset used to train it. In a way, machine learning automates some of the statistical reasoning and pattern matching that the problem solver would traditionally do. The flexibility of the model is the key here. The machine learning field has seen rapid and recent growth. As you start on your machine learning journey, you might see related but different definitions of the terms we will use in this lesson. This is because machine learning is a new field at the intersection of statistics, applied math, and computer science. Each of these fields might have a slightly different formal definition for the same terms. If you want to get more involved with machine learning models, you can use AWS ML services to build, train, and deploy your models fast. Amazon SageMaker, which is a fully managed service, removes complexity from each step of ML workflow. So every developer and data scientist can deploy machine learning for a wide range of use cases, from predictive maintenance to computer vision, with ease at a scale. Let's one more time review the machine learning development workflow. In each of these steps, from collecting data to choosing the right model to model tuning and deployment, you might face some challenges. For example, collecting and preparing data can be time-consuming and undifferentiated, or model training can take a long time and can be costly. Just be ready for these challenges. Challenges are usually good for learning, but in case you want to face no challenges, just know that AWS has some offerings to remove these barriers for your better processes in place. Just be ready for these challenges. Challenges are usually good for learning, But in case you want to face no challenges, just know that AWS has offerings to remove barriers and make the process easier. Amazon built Amazon SageMaker from the ground up to provide every developer and data scientist with the ability to build, train, and deploy machine learning models quickly. You can explore the full list of AWS ML services in AWS Machine Learning webpage. Here I would like to talk about 3 examples of AWS ML services. With Amazon SageMaker, you can build, train, and deploy your model at a scale in a fully integrated development environment. Amazon SageMaker distributed training can automatically partition your model and training data so complicated deep learning models can be developed faster. Amazon SageMaker Clarify can scan your model for biases across the ML workflow, so it brings transparency to your model. These were just 3 examples of many ML services AWS offers. Just make sure you check them out to find solutions that can have more application in your project. Now let's briefly talk about AWS ML infrastructure and framework offering. AWS Workflow Services make it easy for you to manage and scale your underlying ML infrastructure. The next layer highlights that AWS ML infrastructure supports all of the leading ML frameworks. The bottom layer shows examples of compute, networking, and storage services that constitute the foundational blocks of ML infrastructure. But how do we get started with machine learning? This is where AWS has invested in putting machine learning into the hands of developers, literally. We have created a portfolio of educational devices to help put new machine learning techniques into the hands of developers in unique and fun ways. With AWS DeepRacer, you can get hands-on with reinforcement learning. And with AWS DeepComposer, you can collaborate with AI, create music, and learn generative AI.
Hi, I'm Ruchi Binod.
I'm Richard Kalhoff.
I'm Vienna Harvey.
I'm Brian Okeke, and I'm a curriculum manager and self-taught full-stack developer.
I manage our self-driving car here at Udacity.
I'm a content creator and software engineer.
And here at Udacity, I've been developing programs in data science.
Let's discuss strategies for learning new technical skills.
Learning a new skill can be really exciting, but can also be challenging, especially in a self-paced online program.
We start by defining a learning path so that we know what our goals are and that we're making progress towards them.
A goal can be to finish a particular course or complete a nanodegree program and get a new job.
Maybe you're just personally curious about a topic and want to broaden your knowledge base.
Whatever your goal is, try to keep it in mind. It shapes how you learn.
When it comes to goals, one strategy is to set short-term goals and long-term goals. If your goal is to complete a project or apply to a certain kind of job, then you should write an incremental plan to get there.
Knowing specific steps to take or milestones to reach can help you stay on track and not feel overwhelmed.
Take each step as you achieve it so you can see yourself moving closer to your long-term goals.
Keeping yourself accountable to a goal is really important.
Seriously, so important.
Set calendar reminders for yourself to keep yourself accountable and learn some small thing every day. Try to add an additional layer of accountability by telling a partner or friend about it, or even your coworker or boss, someone who can check on your progress.
Enroll in a program with a buddy to help you stay committed to completing the program.
Studies show it takes time to form a new habit, so get into the habit of working on your program.
Once learning becomes a habit, it won't take so much effort to sit down and work on your program. And when you feel like procrastinating, remind yourself why you enrolled in the program in the first place.
To help motivate you.
Then reward yourself when you stick with the habit.
I'd like to get myself an ice cream cone.
Having a plan and checking off smaller items makes the larger task of learning a whole new skill seem a bit more approachable. You can even set a goal of finishing one exercise or part of the lesson in one sitting.
The Udacity Classroom has projects and suggested project deadlines that you can use as well.
While these projects are good milestones, more importantly, they provide hands-on learning to actively practice the skills that you've learned.
Now these projects are meant to be challenging. I know it can be frustrating to get stuck in the middle of a project that is really difficult.
but those times are often the ones where there's more room for exploration and innovation.
For example, when writing a new function, explain the function in simple sentences or pseudocode, and only then move on to writing the syntax. Build on things incrementally.
Everyone struggles a bit when they learn something new. Be patient with yourself.
For example, software programmers in the industry have taken several years to become masters in their domain. So remind yourself of your goal and remember every step is getting you closer to it.
Now, when working with code, there are a lot of great resources for when you hit a roadblock. Making mistakes in your code is actually a great way to learn.
A lot of my own code projects are developed one error at a time.
One habit and skill good programmers have is to read error messages and practice figuring out what exactly is not working in the code.
Being able to use resources to fix your code is a problem-solving skill in and of itself. Community-led sites like Stack Overflow or Udacity's own tool called Knowledge, where people answer each other's questions, can be very useful.
One of the best ways is just to type in an error message into Google and see what comes up.
Because someone else has probably had the same error and maybe figured out a solution.
Also, read blog posts and source code to see how someone else is thinking through a similar problem.
Technical concepts can be hard to learn, and it's normal to get an imperfect solution at the first try.
It's highly recommended to start with something that is small, that works, and incrementally improve it.
Okay, let's summarize.
Set goals for yourself and hold yourself accountable with a schedule or an accountability buddy.
Break down projects into small goals.
Work on incremental parts of the lesson.
Work through exercises to make the learning stick.
And start with pseudocode and use practice and online resources.
You've got this. So good luck.
And happy learning.
Happy learning.
Happy learning.
Happy learning.
Now that you understand the importance of developing in a clean and modular way, let's break down what this means in code. The first tip for writing clean code is to use meaningful, descriptive names for your variables and functions. This can help you explain most of your code without comments. Take a look at this code that initializes a list of student test scores, prints the mean, curves each score by multiplying its square root by 10, and then prints the mean of the new curved scores. With this code, you wouldn't know what was happening right away without these comments. See how this compares to this cleaner code, which conveys the same purpose without the comments. Now we know what both of these lists stand for without the comments, which will help us throughout the program wherever these variables are used. We also use the function with a descriptive name, mean, instead of running a calculation each time. This not only helps readability, but follows the dry principle, or don't repeat yourself, that is important to writing modular code, which we'll talk more about later. In addition, we imported the math module to use its square root method, instead of raising each score to 0.5 with double asterisks, which isn't only more readable, but also faster in Python 3. Try testing how effective your names are by asking a fellow programmer to guess the purpose of a function or variable based on its name, without looking at your code. Coming up with meaningful names often requires effort to get right. Here are some guidelines. Let's start with the first guideline. Be descriptive, and when appropriate, try implying the type of whatever you're naming. Notice we call this list age list instead of ages, which helps us avoid confusing the integer age and the list of ages later in this code. For Booleans, it's often helpful to prefix the name with words like is or has, to make it clear that it's a condition. You can also use parts of speech to imply types by using verbs for functions and nouns for variables. Normally, you don't want to use abbreviations unless the word will be used many times, and you especially don't want single letter names. However, exceptions include names for counters, such as I in this example, as well as common variable names used in math, like x, y, t, and so on. Choosing when these exceptions can be made can be determined based on your audience for the code. If you work with other data scientists, certain variables may be common knowledge, while if you work with full-stack engineers, it might be necessary to provide more descriptive names in these cases as well. However, long names do not always mean meaningful names. You should be descriptive, but not with more characters than necessary. This first example is very verbose. This function computes the number of unique values in a list, regardless of what that list is. So we can generalize and remove of names list from the function name, and replace the argument name with R, which is standard to represent an arbitrary array. In addition, implementation details are unnecessary to include in a function name, so we can remove with set from the function name as well. The resulting function is much more clean and concise, while still being descriptive. Another tip for writing clean code is to use whitespace properly. Code with poor or inconsistent spacing is the worst. Take a look at this mess. If you were handed this code as a developer, the first thing you should do is fix the whitespace and make it consistent. This is much nicer to read and work with. Organize your code with consistent indentation. The standard for Python is using 4 spaces for each indent, unlike we have here. Also be sure to separate sections with blank lines to make it easier to organize and read. And lastly, try to limit your lines to around 79 characters. 79 is the guideline given in the PEP 8 style guide. In many good text editors, there's a setting to display a subtle line that indicates where the 79 character limit is. Notice how much clearer it is to read this Mongo query in this code, with shorter lines and proper indentation. Also notice how much cleaner this ending part of the code is, where we call create plot. For more guidelines on this, check out the code layout section of PEP 8 in the notes below. Let's say you wanted to test a function that finds the nearest perfect square less than or equal to a certain number. Your first approach might be testing it interactively in a terminal or Jupyter notebook, like this. So first we'll import the function from the file, and now we'll start testing it with different values. So let's try 5. That should return 4, since that's the nearest perfect square less than or equal to it. And let's try a negative number, which should return 0, which does. And now let's try an actual perfect square, 9, which should return 9. And let's just try another one, 23, that should return 16. So awesome. While this does test the function, it's still a poor way to test because it isn't repeatable, requires you to type these in manually, and doesn't tell you whether it's returning the correct answers. Imagine you have hundreds of functions you need to test and test repeatedly while iterating on your project. You can see how inefficient and unreliable of a method this approach would be for that. After this, you may consider putting your test code into a file to make it repeatable, and end up writing this. This is better because your test code is now in a file that you can run to repeat the same tests without much work. But it's still not telling you whether it's getting the right answers. You'd still have to check. 5, the lowest one's 4, that's correct. Negative 12, oh yeah, that's 0. Still pretty slow. If we print the correct expected result with each answer, now we do have a clear way to check out the results. However, we still need to check these results manually. You have to compare what they returned and the correct answer yourself. This is not ideal if we're running a large amount of unit tests often. We can use assert to ensure that each result is identical to the correct answer. This is much better since it checks our results automatically. However, look what happens when something fails. Let's say I didn't put this equal sign and I only put a less than sign. The result is messy and it stops the program. Ideally, running a test should run all the unit tests and let you know which ones failed and which ones succeeded. This can't happen if it stops with every failure. Any tests that happened after this one failed, we can't see the results of. In addition, the message for a failure is messier than it needs to be. Fortunately, there are great tools available in Python that we will use to create effective unit tests.
Nearly all tasks solved with machine learning involves three primary components: the machine learning model, the model training algorithm, and the model inference algorithm. These three parts are like the different stages of crafting a teapot from a lump of clay. First, you start with a block of raw clay, which represents your machine learning model. At this stage, the clay can be modeled into many different forms and can be used to serve many different purposes. You decide to use this lump of clay to make a teapot. So how do you create this teapot? You inspect and analyze the raw clay and think about what to change to make it look more like the teapot you have in mind. Much like the artist who gently make adjustments to make the clay look more and more like a teapot, the model training algorithm makes small changes to the model parameters so we achieve our goals. Now you've made your teapot. It's been inspected, evaluated, and now it's ready for your enjoyment. You enjoy your teapot, drink your tea. This represents model inference. Now your model is ready to be used in real world. A model is a generic program made specific by data used to train it. Like a piece of clay, it can be modeled into many different forms and can serve many different purposes. A more technical definition would be that machine learning model is a block of code or framework that can be modified to solve different but related problems based on the data provided. In this example, we are using a linear regression model to predict the number of snow cones you might expect to sell based on the temperature. Our model here predicts that as the temperature increases, you will sell more snow cones. A model can also be used to predict how the number of people who attend college changes based on the cost of admissions. In this example, our model predicts that as the cost of tuition increases, the number of people attending college will decrease. But how does this model do this work? That is what model training is for. The procedure to use data to shape a model for some use cases is called model training. There are many model training algorithms. To understand how they work, let's go back to our flexible lump of clay analogy for a machine learning model. The first thing you would do is inspect and analyze the raw clay and think about how to change it to look more like the teapot you have in mind. Similarly, a model training algorithm uses the model to process data and then compares the results against a goal. In this step, we determine what changes need to be made to get to that goal. Now you shape the clay to make it look more like the teapot you have in mind. Similarly, a model training algorithm gently nudges specific parts in a direction that brings the model closer to achieving the goal. You keep doing these two steps repeatedly. Eventually, you get closer and closer to what you want until you determine that you're close enough to stop. Now you have your completed teapot. It's been inspected and evaluated. It's ready for your enjoyment. So what does this mean from a machine learning perspective? We are ready to use the model inference algorithm to, for example, generate predictions using the trained model. This process is often referred to as model inference. We just described each of these steps in a bit more detail. So let's put it all together. First, you start with a raw piece of clay, which can be modeled into many different things. This represents a machine learning model. Next, you shape your raw piece of clay to make it look like the teapot that you always wanted. Similarly, the model training algorithm gently nudges parameters to make the model capable of solving the problem. Finally, you can enjoy your teapot and put it to work. This represents model inference. You use your model to solve the problem. Now let's go through the lesson outline. You just learned about the different machine learning services AWS offers and what AWS AI devices are. You will then train your reinforcement learning model to race with AWS DeepRacer.
And you will experiment with generative AI algorithm on AWS DeepComposer and will collaborate with AI and will generate music. There is a lot to learn. Let's get started.
Let's get right into it and see how to write a class in Python. If you haven't worked with classes before, the syntax might be a bit confusing, but we'll go through some code step by step. For now, I'm going to show code using Jupyter Notebooks, but later in the lesson, you'll be modularizing code into Python scripts. In the top cell, I've written a shirt class, like what we were just talking about in the previous video. The class has color, size, style, and price attributes. I also wrote a method to change the price, as well as a method to output a discounted price. The code cells that come after this first one show some examples of how to instantiate shirt objects so that you can see how to use a class in a program. I'll start at the top of the file and work down. The very first line tells Python that I'm going to write a class, and then I name the class shirt. Good coding practice says to capitalize the first letter in a class name, but your code will still work even if you don't do this. You can put parentheses after shirt or not. The code will run either way. The next line takes care of initializing all of the attributes with the appropriate values. Remember that a class represents a blueprint. Hence, I'm setting up the color, size, style, and price of a generic shirt. You'll see how the initialization of a specific shirt object works in a minute. There are two things about this that might look a bit funny. The __init__ function, and also the self variable. The init function is built into Python. Python knows to use this function to create a specific shirt object. Again, bear with me for now. I'll go back to this in a minute. The self variable can be tricky to understand at first. Self stores your attributes like color, size, etc., and makes those attributes available throughout your class. Self is essentially a dictionary that holds all of your attributes and the attribute values. Check out the change price method to see how self works. I pass in self as the first method input so that I can have access to the price. Self has the price stored inside it, as well as the other attributes like color, size, and style. Self is always going to be the first input to your methods if you want to access the attributes. Note as well that the change price and the discount methods are like regular Python functions. For example, Python functions do not have to return anything. So like in the change price method, it doesn't return anything. It only changes the value of the price attribute. The discount method, on the other hand, does return something. It returns the discounted price. Again, the shirt class is just a blueprint. I'm going to run this first cell and then move on to the second cell. Let's see how to actually use this class. The following are some examples. If I want to create an actual shirt object, I use this syntax here. This is called instantiating an object. Notice that the syntax and order matches the init function. I'm initializing the specific shirt with the color, size, style, and price, just like in the init function. Python is going to call the init function to initialize this t-shirt object. I'm going to run the code cell. Okay, the output here is a shirt object, and then all of those funny numbers and letters at the end is Python giving the location in memory where the object is stored. But this isn't very useful unless we actually store the object in a variable. So in the next code cell, I'm doing exactly that. I'm going to run this code cell, and now I've stored this shirt object in the variable new shirt. The new shirt variable has a color, size, style, and price associated with it. You can access these attributes using this dot syntax. So I'm going to run this next code cell, and you'll see the output. Scrolling down, you use the same dot syntax to access the methods as well, except you also need to specify any inputs that these methods require. For example, to change the price, I call the change price method with a value of 10. Running this code cell, you now see that the price attribute has changed from 15 to 10. The same goes for the discount method. I input 0.2 to the discount method, and it returns a value of 8 because that's a 20% discount off the price. In this last part, I instantiate 3 shirt objects and then store those objects in a list. The reason I'm showing you this is to emphasize that these variables are like any other Python variable. Here are the results. Once I've stored the shirts into the t-shirt collection list, I then run a for loop and print out the color of each shirt. If you're new to object-oriented programming, all of this might feel overwhelming. My suggestion is to watch this video again and then move on to the next part of the lesson where you can play around with this code and write your own class. The most important thing you can do is practice. Write your own class, run the code, and debug any error messages you get.
If you recall from earlier in the lesson, writing modular code is a necessary practice in software development, where you split your program into logical functions and modules. Let's go over some guidelines to help you with this. First, don't repeat yourself. Modularization allows you to reuse parts of your code. Let's go back to the example earlier on grading test scores. Here, we have a list of test scores that we curve in 3 different ways. Say you're an educator who gave out a test that was too difficult, or gave a question that was a little unfair. So you decide to figure out a way to boost your students' scores. For the first 2 methods, we add a flat curve of 5 points to each score and 10 points to each score. In the third method, we apply a square root curve, where we find the square root of each score and multiply it by 10. Right now, it's difficult to understand what this code is for and looks pretty repetitive. This is an example of spaghetti code, which is common in data scientists and is not something we want to follow. Let's use the tips we learned earlier on writing clean code and improve this with better naming and readable functions. We can represent this list of scores better with something descriptive, like test scores, and use NumPy to get the mean of each list. We can also use list comprehensions to make this more concise and readable, and use more descriptive names for the score and resulting list. Our code is clearer now, but still needs more refactoring. First of all, these lines applying a flat curve of 5 and 10 look awfully similar. We can generalize this in one function, and we can also consolidate all of these print statements into a for loop. This actually demonstrates the next tip. Abstract out logic to improve readability. Notice how abstracting out code into a function not only makes it less repetitive, but also improves the readability with descriptive function names. You can easily guess that this line is applying a flat curve of 5 on a test scores list, and that this line is doing the same thing with 10. And this line applies a different curve using square root. And with this for loop, not only are we removing repeated lines of code, it's also easier to follow what's happening. We are clearly iterating through 4 lists and printing the mean of each. Note that although your code can become more readable when you abstract out logic into functions, it's possible to over-engineer this and have way too many functions. So use your judgment. This leads us to the next tip. Minimize the number of entities, like functions, classes, and modules. There are trade-offs to having function calls instead of inline logic. If you've broken up your code into an unnecessary amount of functions and modules, you'll have to jump around everywhere if you want to view the implementation details for something that may be too small to be worth it. It's kind of the same as naming variables. A longer variable name doesn't necessarily equate to increased readability, the same way creating more modules doesn't necessarily result in effective modularization. Moving on to the next tip, make sure that each function you write is focused on doing one thing. For example, you wouldn't want something like this. This is the same thing we had before, except now each curve function also prints the mean in addition to returning the adjusted list. Avoid having unnecessary side effects in functions and keep them focused. Even if you rename them this way to indicate that they're printing the mean, the functions are still doing multiple things and become more difficult to generalize and reuse. Generally, if there's an "and" in your function name, consider refactoring. Another tip is that arbitrary variable names can be more effective in certain functions. Notice that in these functions, we broke some rules on using descriptive variable names. This is because arbitrary variable names in general functions such as this can actually make the code more readable. Flat curve doesn't actually have to be for test scores. It can be used on any iterable that you want to curve up by a certain integer. While we're on the topic of writing simple and focused functions, another useful tip is to make sure that you use no more than 3 arguments when possible. Of course, this is not a hard rule, and there are times it's more appropriate to use many parameters. But in the vast majority of cases, it's more effective to use fewer arguments. Remember, we are modularizing to simplify our code and make it more efficient to work with. If your function has a lot of parameters, you may want to rethink how you're splitting this up. With this small example, you saw how functions can be used to abstract out parts of a program to make it more readable, clear, and reusable. This becomes more essential the more complex your algorithms are, especially in data science work. PyTest is a great tool that lets you start testing quickly without any boilerplate code. To install it, pip install PyTest like this in your terminal. Once you have PyTest installed, all you have to do is create a test file and write a function for your unit test. Then, enter PyTest in the directory of your test file. Each dot next to the name of the test file represents a successful test. If you made a mistake in your function and one of your tests fail, the dot will be replaced by an F, and the error will be shown below. Notice your tests won't be stopped by failed assert statements. It continues to run the test after this failed one, but it will stop if you do have syntax errors. It's wise to have only one assert statement per test. Otherwise, you wouldn't know exactly how many tests failed and which tests failed, since all you see is what test functions failed. Another important note is that you have to start your test files with test underscore and your test functions with test underscore as well, for PyTest to recognize and run them. This is the default. If you wish to change this, you can do so by learning about the PyTest configuration in the link below.
Regardless of a specific model or training algorithm used, many people working in machine learning space use a common workflow. The steps in this workflow are defining the problem, building a dataset, training the model, evaluating the model, and using the model. The remainder of this lesson will be centered around each step in this process. We will talk about different potential pain points and common tasks machine learning practitioners do at each step.
Welcome to Reinforcement Learning with AWS DeepRacer. My name is Eva Pagneux, and I'm a product manager with AWS DeepRacer. In this section, we'll introduce reinforcement learning and talk about its real-world applications. Then, we'll take a closer look at the basic concept of this type of machine learning using AWS DeepRacer as an example. By the end of the section, you will be able to create, train, and evaluate a reinforcement learning model in the AWS DeepRacer console. Let's get rolling! Reinforcement learning is one of 3 major types of machine learning, a subset of artificial intelligence. Reinforcement learning is learning what actions to take in a situation so as to maximize rewards, in the form of a number on the way to reaching a specific goal. The agent learns through discovering which actions yield the most reward. This is modeled virtually, but the digital model can be transferred to a physical device. We'll talk about 2 fields where reinforcement learning is used today to solve real-world problems. First, to understand reinforcement learning, it's helpful to think about training a dog. You reward positive behavior and discourage negative behavior. Over time, your dog learns to choose actions that result in more treats, and you see more of the behavior that you incentivized. Training your computer software using reinforcement learning leverages this exact idea, using numerical signals instead of clicks or treats.
There are a couple of notes I wanted to mention about object-oriented programming. In the first part of the lesson, you'll be doing coding exercises in Jupyter notebooks. When writing software, however, you generally wouldn't write object-oriented programs in a Jupyter notebook. Instead, you would modularize the code into separate Python scripts. In the second half of the lesson, you'll be modularizing code. So here, I'm going to give a preview of what's to come later in the lesson. If you haven't seen this particular interface in other Udacity courses or lessons, this is called a workspace. It's embedded in the classroom, and you'll use it later in the lesson. This is a Linux Ubuntu environment where you can write and execute Python code. In one file, I've put the shirt class code and called the file shirt.py. Now I'm going to write a separate Python script that uses the shirt class code. In the same folder, I've created another file called example.py. Inside example.py, I want to use the shirt class. First, I need to import the shirt class, typing from shirt import shirt. The lowercase shirt refers to the shirt.py file. The uppercase shirt refers to the class defined inside this file. I could name the file and class anything I wanted to. They don't have to be the same. I just did this for convenience. Now, in example.py, I can use the shirt class just like what you did in the previous exercise. The difference is that the code is now modularized. I'll write some code that uses the shirt class. And finally, I'm going to run the code in the terminal. First, I'm going to change the directory I'm in to make sure I'm in the directory with the Python files. And then I'm going to type python example.py. Okay, so the output are the print statements I had in the code. On a separate topic, I wanted to mention how to access attribute values and change attribute values in Python. The shirt class has a method to change the price of the shirt. Like you can see in line 9 in example.py, shirt_2.changePrice 45. In Python, you can also change the values of an attribute with the following syntax. Shirt_1.color equals red. Shirt_1.size equals large. Let me go back. The shirt 1 is already red, so let's say yellow. And shirt1.price equals 43. There are some drawbacks to accessing attributes directly versus writing a method for accessing and displaying attributes. In terms of object-oriented programming, the rules in Python are a bit looser than in other programming languages. In some languages, like C++, you can explicitly state whether or not an object should be allowed to change or access an attribute's values directly. Python does not have this option. Why might it be better to change a value with a method instead of changing a value directly? Changing values via a method gives you more flexibility in the long term. What if the units of measurement change, like the store was originally meant to work in US dollars and now has to work in euros? Here's what I mean. If you've changed an attribute directly, like in line 14, if all of a sudden I have to use euros, I'm going to have to manually change this to say 38. You're going to have to do this wherever you access the price attribute directly. If, on the other hand, you would use a method like the change price method, then all you have to do is go into the shirt class and change the original method one time. I'm just going to multiply by 0.81 to convert everything from dollars to euros. Now if you go back to example.py, a line like number 9, you don't have to manually change the price from dollars to euros because the conversion is going to take care of that for you in the shirt class. For the purposes of this introduction to object-oriented programming, you will not need to worry about updating attributes directly versus using a method. However, if you decide to further your studies of object-oriented programming, especially in another language such as C++ or Java, you'll have to take this into consideration. Now that you've practiced working with all of this new syntax, let's get to the exciting part. In the rest of this lesson, you're going to learn more about object-oriented programming and then use those skills to build a Python package. The package will contain code to analyze Gaussian distributions. You can use the package to read in a data set and calculate the mean and standard deviation. You'll also include code to plot a histogram of the dataset as well as a probability density function of a Gaussian distribution. And finally, this package will be able to add two Gaussian distributions together. I'm going to start by giving you a tour of what the code looks like and how the code works. Then you'll build up the code yourself. At the end of the lesson, you're going to extend the package to also handle binomial distributions. The best part about this lesson is that you will have an actual functioning Python package that you can pip install using the terminal. If you want, you can even upload the package to PyPy, where Python packages are stored for the general public to download and install. This lesson assumes that you're familiar with Gaussian, also known as normal distributions, as well as binomial distributions. I'll put some resources below if you feel like you need to review them. With that, let's start looking at some code.
Test-driven development is when you write tests before you write the code that's being tested. This means your test would fail at first, and you'll know you've finished implementing a task when this test passes. This way of developing code has a number of benefits that's made it a standard practice in software engineering. As a simple example, let's say you have to write a function that checks whether a string is a valid email address. You think of a few factors to consider, such as whether the string contains an @ symbol and a period, and write out a function that addresses them, and then test it manually in your terminal. You input one valid and one invalid email address to make sure it works properly, and it does. You try a few more valid and invalid email addresses, and one of them gives back the wrong result. You realize you forgot to consider an edge case in your function, so you go back and add that in. Then you test your function with another edge case you forgot to consider, and edit your function again to fix this. Instead of doing all of this back and forth, you can try to create a test that checks for all the different scenarios and edge cases you can think of before even starting to write your function. This way, when you do start implementing your function, you can run this test to get immediate feedback on whether it works or not in all the ways you can think of as you tweak your function. If your test passes, you know your implementation is done. In the future, when you refactor this function or make changes to other parts of your program, you can keep running this test to ensure your function still behaves as expected. This also helps ensure that your function behavior is repeatable, regardless of external parameters, such as hardware and time. When you first start writing tests, you will be slow, and you will be tempted to write implementation code before you write tests. Stick with it though, and through practice, you will get faster. Eventually, you'll be able to write all kinds of tests in very little time. When you refactor, it's important to improve the efficiency of your code in addition to making it clean and modular. There are two parts to making code efficient: reducing the time it takes to run and reducing the amount of space it takes up in memory. Both can have a significant impact on a company or product's performance, so it's important to practice this. It's especially important if you'll be working in a production environment. However, it should be noted that how important it is to improve efficiency is context dependent. Slow code might be passable in one case and not another. For example, some batch data preparation processes might not need to be optimized right away if it runs once every 3 days for a few minutes. On the other hand, code used to generate posts to show on a social media feed needs to be relatively fast, since updates happen instantaneously. Again, you may spend a lot of time refactoring to clean or optimize your code after you already have something working. It's important to understand how valuable this is for your work and yourself as a developer. Each time you optimize your code, you'll pick up new knowledge and skills which will make you a more efficient programmer over time. Let's see a few examples of inefficient code and practice refactoring to optimize their performance.
The first step in the machine learning workflow is to define the machine learning problem you are trying to solve. You might be wondering, how we even start to define a machine learning task? First, we define a very specific task. Think back to our snow cone example. Now imagine that you own a frozen treat store and you sell snow cones along with many other products. You wonder, how do I increase sales? This is not a specific task. It is too broad. A machine learning practitioner might frame the problem differently, such as, does adding $1 upcharge for sprinkles on a hot fudge sundae increase the number of snow cones sold? Or another example, does adding a 50-cent upcharge for mixing flavors increase the number of snow cones sold? Next, we want to identify the machine learning task we should use to solve this problem. This will help us better understand the data we need for the proposed project. We will look at some examples in more detail. What exactly are machine learning tasks? All model training algorithms and the models themselves take data as their input. The outputs, however, can be very different. They can be classified into different groups based on the machine learning task. The characteristics of the input data actually help define which machine learning task can be used. Two common machine learning tasks are supervised and unsupervised learning. We have reinforcement learning as well, as we briefly talked about it before, but you will learn about reinforcement learning in a later lesson. One way to break down these machine learning tasks is based on the type of data you need to train your model. Most data can be described as either labeled or unlabeled data. So what is the difference? Let's talk about supervised learning first. We use the term labeled data to refer to data that already contains the solution, called labels. Let's think back to our snow cone example. What were we trying to predict? We were trying to predict the number of snow cones we would sell. Those data points are solutions, or labels. We use both the number of snow cones sold and the temperature to generate the best fit line on the graph. Another type of machine learning task is unsupervised learning. As you might guess, we call data unlabeled when we don't have the solutions or labels. Let's look at a couple of examples here. Take a quick look at this picture. What do you see? Your first thought might be a tree. You just labeled this picture, but a computer initially only sees that image as a matrix of pixels which represents that image, not the whole image. Here's another example. Imagine that you work for a company that recommends books to readers. To provide better recommendations to your readers, you want to discover unknown macrogenres. You are fairly confident that these genres exist. It would be impossible for you to read every book in the world to ensure that a particular macrogenre exists. But words and phrases used in the book description might provide some guidance on which macrogenre a book belongs to. Because you don't know which macrogenre exists, you cannot use supervised learning technique here. You don't have labels. Instead, you can use a common unsupervised learning technique called clustering to determine if books have some natural grouping. We will take another look at this example of unsupervised learning in a real-world scenario later in this lesson. Just as we initially divided a task based on whether we had labeled data or not, we can continue to further define the machine learning task based on the type of label. Imagine that we trained a machine learning model to predict the type of a flower based on images. In this example, our label is categorical. We are performing a classification task. In our snow cone example, we were trying to predict the number of snow cones sold on a given day based on a temperature. Our label is a number that could in theory be anything. In that case, we are performing a regression task. These are just two of the most common examples. You will find many other types of supervised learning tasks as you explore the machine learning space. Similarly, with unsupervised learning, you can further narrow the scope of the machine learning task you're working on. In our book macro genre example, clustering is one common application of unsupervised learning. As you explore the machine learning space, you will find many other types of unsupervised learning tasks, such as neural networks.
Today, reinforcement learning is used in a variety of fields to solve real-world problems. It's particularly useful for addressing sequential problems with long-term goals. Let's take a look at a couple examples. Reinforcement learning is great at playing games. Famously, the AlphaGo Zero software used reinforcement learning to defeat the human master Lee Sedol in the notoriously complex board game Go. Reinforcement learning is also great at Atari and reached another AI milestone when the AlphaStar software achieved Grandmaster status in the real-time strategy video game StarCraft II. But did you know that reinforcement learning is also used to create games? Video game level design determines how complex each stage of a game is and directly affects how boring, frustrating, or fun it is to play that game. If a game is too easy, it's boring. It's too difficult, too frustrating. But if you can get the balance just right, you're rewarded with worldwide communities of dedicated fans. It takes a lot of experience and a deep understanding of a game's content to find the best challenge ratio for a level. To gather the data, highly skilled designers spend a lot of time testing each game. That's where reinforcement learning comes in. The agent plays the game over and over again to collect data which can be visualized on graphs. This visual data gives designers a quick way to assess how easy or difficult it is for a player to make progress, which enables them to find that just right balance between boredom and frustration faster. Reinforcement learning models can also be used to power robotics in physical devices. When multiple turbines work together in a wind farm, the turbines in the front, which receive the wind first, can cause poor wind conditions for turbines behind them. This is called wake turbulence, and it reduces the amount of energy that is captured and converted into electrical power. Clean energy organizations around the world are using reinforcement learning to test solutions. Their models respond to changing wind conditions by changing the angle of the turbine blades. When the upstream turbines slow down, it helps the downstream turbines to capture more energy. Other examples of real-world reinforcement learning include industrial robotics, fraud detection, stock trading, and of course, autonomous driving.
Let's go through an example scenario where we optimize some code to be more efficient. Say we are managing books for a store, and we want to find all the books published within the last 2 years about code. We have a file that lists all the IDs of books published in the last 2 years, called bookspublished last2years.txt, as well as a file for all coding books, allcodingbooks.txt. Since we want to find all the coding books published within the last 2 years, we'd want to find the book IDs included in both of these files. Your coworker came up with one approach and shows you this code to find the books in both files. After reading in the files, their strategy is to loop through each book in the first file, check if it's contained in the second file, and if so, add it to the final list. This makes sense and is an intuitive first approach. Let's see how long it takes to run. So that took about 13.6 seconds. There are several things we can do to make this more efficient. Here are some tips. First, use vector operations over loops when possible. NumPy and Pandas are your best friends for this. There are many cases in which you can replace loops with NumPy and Pandas functions that use vector operations to make your computations a lot faster. Sometimes there's a method that does exactly what you need. Other times, you need to be a little creative. This example in particular has a useful method you can use. Let me show you how I would approach this. No joke, I Google how to find common elements in two NumPy arrays, and here are the results I get. Use NumPy's intersect1d method to get the intersection of the recent books and coding books arrays. I'll give you this same notebook, and I'll put a cell right here with code to record the time it takes to run. Write your line of code in this line. The second tip is to know your data structures and which methods are faster. In addition to relying on NumPy and Pandas, it's often good to double check whether there's a data structure or method in Python that you can use to accomplish your task more effectively. For example, in this case, do you recall a data structure in Python that stores a group of unique elements and can quickly compute intersections and unions of different groups? Sets. You can read more about why sets are more efficient than lists for this task in the link at the bottom of this page. Also, remember how I said I Googled everything? Last time, I was Googling how to find common elements in specifically NumPy arrays. But you can go even more general and Google something like how to find common elements in two lists Python, and you'll see posts like this that share and compare different answers. You can see the set being introduced here. This seems to have a lot of votes, but ultimately we should try different methods and compare their efficiency for our example. Because different methods perform differently in different contexts, it's smart to always test for yourself. In the next cell of the Jupyter Notebook, find out how long it takes to compute the common elements of recent books and coding books using the Python sets intersection method. Here again is some code to measure how long it takes.
To start off, you're going to look at a Python class I've written called Gaussian, and then you're going to code this on your own. You can see that the class has an init method for instantiating an object. There are 3 attributes: mean, standard deviation, and an empty list for storing data. Notice that the init function includes a default value of 0 for the mean and 1 for the standard deviation. This is like any other Python function where you can specify default values for the inputs. Notice as well, the init has no input for the data attribute. A class attribute does not need to be included in the init input variables. Then I've defined a handful of other methods to calculate the mean of the data, for example here, the standard deviation of the data here, and a method to read in a data file called readDataFile. There are a few other methods as well that we'll get to in a minute. Looking at the readDataFile method, you can see that this method reads data from a file and then stores the data in the data attribute. There's something particularly interesting about the readDataFile method. This code actually calls the calculateMean and calculateStandardDeviation methods from the self variable and then stores the results in the mean and standard deviation attributes. The self variable not only gives you access to the class attributes, but also to the class methods. The Gaussian class has a couple of other methods as well. One plots a histogram using the matplotlib package. I've also included a function for outputting the results of a probability density function, and a plot of a normalized histogram with a probability density function in the same x value range. These are just to give more examples of how you can use class methods. Next, I actually use the class by instantiating an object called Gaussian1. Here I'm going to run that code cell. Because I haven't specified any parameters, the default mean and standard deviation are used. There's a data file called numbers.txt in the same folder as this Jupyter Notebook. So I read in the data from that file and then use the other methods to output a couple of plots. In this next part of the lesson, I'm going to give you a skeleton version of this Gaussian class with a few sections marked to do. This is what it looks like. Your task is to fill out the code. The code is already in this video you just went through, but try not to peek back at this video. Follow the comments in the to-do sections and see if you can code the Gaussian class on your own. The file you're going to work with also contains unit tests that you can run to help check your work. They're at the bottom of the file. Let me show you how that works. So if you run this first code cell up here, then you can execute this second code cell, and it'll show you the results of all the unit tests. It says that I have a few errors, a few failed tests, so I need to go back and work on the code. Writing code that you've already seen might seem like a silly exercise, but it should help solidify your understanding of how object-oriented programming works in Python. You'll work on a more challenging coding assignment at the end of the lesson. For now, see how much of the Gaussian class you can rewrite on your own. But don't worry, I've also included an answer file as part of the code.
Being able to log well is a very useful practice in software engineering, and especially useful in data science. Imagine you're running a model every night, and when you come into work one morning, you see that it crashed or started creating poor results. You want to check the cause, the context, and figure out how to address the issue. Since you weren't physically there to see and debug when the issue occurred, it's important to print out descriptive log messages to help you trace back your issue and understand what's happening in your code. In the next video, we'll look at some examples of good log messages and see useful logging tools available to us.
The next step in the machine learning workflow is to build a dataset that can be used to solve your machine learning-based problem. Working with data is perhaps the most overlooked yet most important step of the machine learning process. Forbes did a survey back in 2016 which showed that about 80% of machine learning engineer time is spent preparing data. Understanding the data we are working with, really understanding it, helps us select better models and algorithms that ultimately enable us to have a more effective machine learning solution. There are 4 ways to break down the data portion of the machine learning workflow: data collection, inspection, summary statistics, and data visualization. Each plays an important role. Let's take a deeper look at each step. The first step is to gather data relevant to your problem. For example, if you're trying to build a system to detect if a cat is present in an image or not, you could take a lot of pictures, some of which contain cats or some of which don't. Note that you can find a lot of public data sets, so you might try some quick internet searches if you're still early in your exploration. The format, whether it is labeled or unlabeled, and the availability of data will ultimately determine the machine learning tasks you can solve. Now that you have some data, it's essential to inspect the integrity of the data. Don't assume any data you find is high quality. The quality or lack thereof will ultimately have a massive impact on how well you can expect your model to perform. As you explore your data, you're trying to identify anything that's outside the norm. You're also looking for any missing or incomplete data. This could be very important information. Many models prefer numeric data. The question is, does any of the data need to be transformed to be able to work with the model type you're working on? A great way to better your data is to use summary statistics and create data visualization. For example, take a look at this fictionalized data. You can very clearly see different clusters of data here. Summary statistics allow you to see trends in your data, which can help you better understand what the data is communicating. There are many statistical tools you can use to calculate things like mean, inner quartile range, or short form IQR, and a standard deviation. These tools can give you insight into the scope, scale, and shape of the dataset. You might also detect outliers that you might have missed using other methods.
In this section, we'll learn some basic reinforcement learning terms and concepts using AWS DeepRacer as an example. Now, let's look at some basic reinforcement learning terms and concepts. You'll see how they all come together to make an AWS DeepRacer model later in this lesson. The piece of software you're training is called an agent. It makes decisions in an environment to reach a goal. In AWS DeepRacer, the agent is the car, and its goal is to finish laps around the track as fast as it can, while, in some cases, avoiding obstacles. The environment is the surrounding area our agent interacts within. For AWS DeepRacer, this is a track. The state is defined by the current position within the environment that is visible or known to an agent. In AWS DeepRacer, each state is an image captured by the camera. And the initial state for a car is the starting line of the track, and the terminal state is when the car finishes a lap, bumps into an obstacle, or drives off the track. For every state, an agent needs to take an action towards achieving its goal. Some actions a car can take when it approaches a turn are accelerating, braking, turning left, right, or going straight. Feedback is given to an agent for each action it takes in a given state. Unlike dog tricks, this feedback is a numerical reward. In AWS DeepRacer, a reward function is an incentive plan that assigns numerical rewards to different zones of the track. An episode represents a period of trial and error when an agent makes decisions and gets feedback from its environment. For DeepRacer, an episode begins when the car leaves the starting position and ends at the terminal state, when it finishes a lap, bumps into an obstacle, or drives off the track. Now, let's see how these concepts work together during the training process. In a reinforcement learning model, an agent learns in an interactive, real-time environment by trial and error using feedback from its own actions. Feedback is given in the form of rewards.
Code reviews are a common practice at work, and for good reason. Reviewing each other's code can help catch errors, ensure readability, check that standards are being met for production-level code, and share knowledge among a team. They are beneficial for the reviewer, the reviewee, and the team. Ideally, a data scientist's code is reviewed by another data scientist, since there are certain errors and standards to check for specifically in data science. For example, data leakages, misinterpretation of features, or inappropriate evaluation methods. Let's walk through an example of conducting a code review. Documentation is additional text or illustrated information that comes with or is embedded in the code of software. Documentation is helpful for clarifying complex parts of your program, making your code easy for yourself and others to navigate, and quickly conveying how and why different components of your program are used. There are several types of documentation you can add at different levels of your program. First, you can add documentation at the line level, using inline comments to clarify your code. Second, you can add documentation at the function or module level, using docstrings to describe its purpose and details. Finally, you can add documentation at the project level, using various tools such as a README file to document details about the project as a whole and how all the files work together. In the next few sections, we will practice using these different modes of documentation and learn best practices to make sure our documentation is effective and useful.
Great work coding the Gaussian class. The more you practice writing object-oriented code, the better you'll get at it. Thinking about Gaussian distributions, do you know what it means to add two Gaussian distributions together? The math is straightforward. Let's say you have a Gaussian distribution and another Gaussian distribution. You want to sum these together. To find the mean of this new distribution, you add the means of the individual Gaussian distributions together. To calculate the standard deviation, you take the square root of the sum of squares of the standard deviations. Mathematically, there's a clear definition of what it means to sum two Gaussian distributions. But what about in your code? If you instantiate a Gaussian object and then instantiate another Gaussian object, can you type out Gaussian A plus Gaussian B and expect to get the correct result? No, Python doesn't have any idea how to add two Gaussian distributions together. This code is going to produce an error. What if I told you that there was a way to tell Python how to add two Gaussian distributions together? You could type Gaussian A plus Gaussian B and then get a new Gaussian object containing the correct mean and standard deviation. That would be quite magical, wouldn't it? Well, Python has a feature called magic methods that are specifically for overriding default Python behavior. And in the next part of the lesson, you'll practice writing magic methods.
Now we can finally start training our model. One quick step before training your model is splitting your dataset. You need to randomly split the dataset, keeping some of the data hidden from training. This enables you to later evaluate your model with the data before it's put into production. A training dataset is the data that will be used when your model is training. Most of your data will be here. A general rule of thumb is around 80% of your data. There's also a test dataset. This is the data that the model hasn't seen during training. It's used during the model evaluation stage. It helps you see how well your model will generalize to new data. As you learn more about machine learning, there are additional components, such as validation data. Those are outside the scope of this lesson, but just keep them in mind. What exactly is model training? Let us start with a general definition. The model training algorithm iteratively updates the model parameters to minimize some loss function. Let's unpack that one. Model parameters are setting, knobs, or configurations that the training algorithm can update to change how the model behaves. Depending on context, you'll also hear other more specific terms used to describe model parameters, such as weights or biases. Taking a look at this snow cone example, since we were trying to fit a linear function to this data, the parameters would be the orientation and location of the line. Nearly all models are trained by slowly changing model parameters to move the model closer and closer to achieving some goal. A loss function is used to codify the model's distance from this goal. For example, if you were trying to predict number of snow cone sales based on the day's weather, you care about making predictions which are as accurate as possible. So you might define a loss function to be something like the average distance between your model's predicted number of snow cones sold and the actual number. Here's a concrete example. Imagine that your model predicts you would sell 12 snow cones on a day where the temperature is 95. Our historical data shows the number of snow cones sold is 15. The difference between 12 snow cones predicted and 15 actual snow cones sold, which is, as you can see, is 3, is what the loss function seeks to minimize. In practice, you will likely use one of several common loss functions for most problems. Of course, there are plenty of other details involved in the process. Let's touch on a few high-level questions you might have and a few useful things to know. As you grow your familiarity with this space, you will learn a few common model training algorithms. You could absolutely implement these from scratch, but unless you're developing brand new models or algorithms, you will likely use one of many machine learning frameworks which already have these implemented for you. Determining which model to use, a process known as model selection, is not a perfect science. The list of established models is constantly growing, and even seasoned machine learning practitioners will try many different types of models while solving a problem with machine learning. Within this course, you will see a few types of models at the end of this lesson while walking through some real-world example. Oftentimes, a model or a training algorithm will have settings called hyperparameters, which cannot be changed during model training. These settings can affect how quickly or how reliably the model trains. You will see this across many steps in this process, but be prepared to iterate. Pragmatic problem solving with machine learning is rarely an exact science. Often you might have assumptions about your data or assumptions about the problem, which turn out not to be true. Don't get discouraged. Instead, foster a habit of trying new things and measure success in a way that lets you compare results across iterations.
AWS DeepRacer may be autonomous, but you still have an important role to play in the success of your model. In this section, we introduce the training algorithm, action space, hyperparameters, and reward function, and discuss how your ideas make a difference. An algorithm is a set of instructions that tells a computer what to do, and, as we discussed earlier, machine learning is special because it enables computers to learn without being explicitly programmed to do so. However, computers aren't naturally motivated by rewards in the same way dogs are motivated by treats. So the training algorithm's job is to tell the computer it wants rewards, lots of rewards. In other words, the training algorithm defines your model learning objective, which is to maximize total cumulative reward. Different algorithms have different strategies for going about this. Choose from 2 algorithms with distinct strategies for accomplishing the learning objective of maximizing rewards when you build your AWS DeepRacer training model: Soft Actor Critic, SAC, or Proximal Policy Optimization, PPO. SAC embraces exploration, is data efficient, but can lack stability. PPO is stable, but data hungry. The set of all valid actions or choices available to an agent as it interacts with an environment is called an action space. In the AWS DeepRacer console, you can train agents in either a discrete or continuous action space. A discrete action space represents all of an agent's possible actions for each state in a finite set of steering angle and throttle value combinations. A continuous action space allows the agent to select an action from a range of values that you define for each state. The SAC algorithm only works in a continuous action space. PPO, however, works in both continuous and discrete action spaces. Hyperparameters are variables that control the performance of your agent during training. There is a variety of different categories to experiment with. Change the values to increase or decrease the influence of different parts of your model. For example, the learning rate is a hyperparameter that controls how many new experiences are counted in learning at each step. A higher learning rate results in a faster training, but may reduce the model's quality. You also play a crucial role through the design of your reward function. Its purpose is to encourage the agent to reach its goal. Figuring out how to reward which actions is one of your most important jobs.
The first mode of documentation we'll talk about are inline comments. By now, you've probably seen this many times. Text following a hash symbol throughout your code. They're used to explain parts of your code and really help future contributors understand your work. There are different ways comments are used, and definitely differences among great comments, okay comments, and even useless comments. One way comments are used is to document the major steps of complex code to help readers follow. For example, With the guiding comments in this function, you don't really need to understand the code to follow what this function does. If I was seeing this for the first time and had no idea what these functions or tools were, these comments really help me understand the purpose of each block of code and even help me figure out individual lines of code or methods. However, others would argue that this is using comments to justify bad code, and that if code requires comments to follow, it's a sign refactoring is needed. Comments are valuable for explaining where code cannot. For example, the history behind why a certain method was implemented in a specific way. Sometimes an unconventional or seemingly arbitrary approach may be used because of some obscure external variable causing side effects. These things are difficult to explain with code. These numbers for detecting edge levels in an image may seem arbitrary, but the programmer experimented with different numbers and realized that this was the one that worked for this specific use case. Congratulations on completing this lesson on software engineering practices. This was just an introduction, as this is a very large set of skills that you should work on continuously. By getting through this lesson, you've made a good start to your development of software engineering skills. I encourage you to research further and practice using these skills as you continue your path to becoming a great data scientist.
Besides the methods shown in a previous video, I've added 2 more methods to the Gaussian class. These are the add method and the REPR or representation method. These are both called magic methods. The syntax might look somewhat familiar because you've actually already worked with a magic method. The init function, which initializes a new object, is a magic method. Magic methods let you override and customize default Python behavior. For example, the init method lets you customize how Python instantiates an object. The add method overrides the behavior of the plus sign. I'm going to execute the code cell with the Gaussian class. Below, I've instantiated 2 Gaussian objects, and then I add them together. Python knows how to add 2 floats together or 2 integers together. These operations are defined as part of a Python installation. Adding a Gaussian to a Gaussian, however, has no meaning in Python, so this code should produce an error. I'm going to run it. Well, the code didn't produce an error. That's because I've defined the behavior of adding 2 Gaussians together. Scrolling back up to the add magic method, you can see how this works. The function has 2 inputs, self and other. Self refers to the object to the left of the plus sign. Other refers to the object on the right side of the plus sign. I can then define what it means to add these 2 objects together. Adding 2 Gaussians together sums the means together and takes the square root of the squares of the standard deviations. Then the code instantiates a new Gaussian object with the new mean and the new standard deviation and returns the new object. For another example, consider the representation method. In Python, do you remember what happens when the only code on a line is a variable? Python will print out the value of the variable. So if I say x equals 5 and then just execute x, Python prints out the value 5. The representation magic method controls what gets printed out. So here the code overrides the default representation behavior to print out the mean and standard deviation of the Gaussian object. Here I'm going to run this line of code so you can see the results. Python has dozens of magic methods. You can override the plus sign, minus sign, division, multiplication, greater than, and less than symbols, just to give a few more examples. To get practice with magic methods, you'll go back to the Gaussian method and rewrite the code you've just seen. If you're getting tired of rewriting code, not to worry. Soon, you'll be converting this Gaussian module into an actual package and then adding more functionality.
After we have collected our dataset and trained our model, we are ready to actually see how well our model works. Let's start with an example. Let's say there is a dataset containing data on many different aspects of flowers, like petal length or color. Let's say you're building a model to determine if a flower is one of 2 common species based on measurable details. You could use model accuracy or how often your model predicts the correct species to evaluate if your trained model will be good at solving that task. To evaluate models, we often use statistical metrics like accuracy. Here are a few examples of different metrics that you can use. Some are more common than others. For example, precision or F1 score. But there are more that you can explore. Please note that this is not a one and done process. It's an iterative process until you get the results you're looking for. Based on how the model evaluation goes, you may find that you need to go back to previous steps that we discussed. You might need to change the configuration of parameters of the training model or possibly even choosing different model. You might have to tweak the model or make adjustment to your data. You might even rethink how you're framing the problem. At some point, you will have a model which meets your need. Now you can use the model.
Now, let's put these ideas into actions. In AWS DeepRacer's training environment, you can imagine the reward function as a grid mapped over the racetrack. Each square is a state. The green square is the starting position, or initial state. And the finish line is the goal, or terminal state. Each state is assigned a score by your reward function. You incentivize behavior that supports your car's goal of completing fast laps by giving the highest numbers to the parts of the track you want it to drive on. The squares containing X's are the track edges and defined as terminal states, which tell your car it has gone off track. The reward function is actual code you'll write to help your agent determine if the action it just took was good or bad, and how good or bad it was. This reward function is incentivizing centerline driving. Exploration versus exploitation is a key challenge in reinforcement learning. When a car first starts out, it explores by wandering in random directions like the car on the left. However, the more training an agent gets, the more it learns about its environment. The experience helps it become more confident about the action it chooses. The car on the right has begun to exploit or use information from previous experiences to help it reach its goal. Different training algorithms utilize exploration and exploitation differently. Let's see what exploration and exploitation look like using our visualization of a reward function that incentivizes for centerline driving. The car starts out by wandering around the track and learn about its environment. The longer it trains, the more experience it gains. Eventually, it begins to maximize its rewards by driving down the center of the track. While training your car in the AWS DeepRacer console, your training metrics are displayed on a reward graph. Plotting the total reward from each episode allows you to see how the model performs over time. The more reward your car gets, the better your model performs. So let's take another look at how these concepts work together during the training process. As we said before, our agent learns in an interactive, real-time environment by trial and error using feedback from its own actions. Feedback is given in the form of rewards. In the case of AWS DeepRacer, the car is the agent. During training, it interacts with a simulated racetrack environment. Its overall goal is to get to the finish line while maximizing its total reward. The rewards are numbers that you assign to different zones of the track when you design your reward function. DeepRacer takes about 15 pictures per second as it drives around the track. Each image represents a state. After each picture, DeepRacer takes an action, like changing its speed or steering angle. The process we just described happens over and over again because learning takes practice. The more the car goes around the track, the more experience and knowledge it collects. The more knowledge it gets, the smarter it gets. Just like a dog learns how to behave to collect more treats, the car here, our agent, will learn how to maximize the rewards in each state and action. Both dogs and cars use what they learn to make future decisions. In the case of AWS DeepRacer, once training is finished, you have a model that you can submit to the virtual AWS DeepRacer League or upload it to a physical agent, the AWS DeepRacer device, that will then use the model to navigate a physical track in the real world. So now that you've had an introduction to reinforcement learning, it's time to get started building your own model with AWS DeepRacer. DeepRacer is a combination of a physical car, a virtual simulator in the console, the AWS DeepRacer League, and community races. A DeepRacer device is not required to start learning. You can start now in the AWS DeepRacer console. The 3D simulator in the AWS DeepRacer console is where the training and evaluation take place. We'll explore in detail how to create your model next. Once your model is ready, you can either submit it to the AWS DeepRacer League, or you can create your own race for your own organization using the community race feature. Let's get started.
Doc strings, or documentation strings, are valuable pieces of documentation that explain the functionality of any function or module in your code. Ideally, all of your functions should have doc strings. Here's a function for population density. A doc string is always surrounded by triple quotes. If you feel that this one line of documentation is sufficient for you to end the doc string at this point, single-line doc strings are perfectly acceptable. If, however, you think that the function is complicated enough to warrant a longer description, you can add a more thorough paragraph after the one-line summary. The next element of a doc string is an explanation of the function's arguments. Here, you list the arguments, state their purpose, and state what types the arguments should be. Finally, it's common to provide some description of the output of the function. Every piece of the docstring is optional. However, docstrings are a part of good coding practice. They assist you and future users of your code in understanding the code you produce. You can read a more thorough explanation of docstring conventions in the link below.
There's one more object-oriented topic to cover in this lesson: inheritance. I think inheritance is easier to understand using a real-world object, like the shirt example from earlier in the lesson. The shirt had 4 attributes: a color, size, style, and price. And the shirt also had 2 methods: a method to change the price and a method for calculating a discounted price. As the store expands, it might stock other types of clothing like pants, socks, and dresses. These garments have a few attributes and methods in common with the shirt object. They'd probably all have a color, size, style, and price, and they could all use functions to change the price and calculate a discount. Why code separate classes for each new garment when they all have so much in common? Instead, you could code a parent clothing class, and then the pants, socks, dresses, and shirt classes could inherit the attributes and methods of the clothing class. This looks like a family tree where clothing is the parent and pants, socks, dresses, and shirts are the children. One benefit is that as you add more clothing types like blouses, you can easily add a new class that inherits from the clothing class as well. What if you wanted to add a new attribute like material to represent if the garment is made of cotton, nylon, or some other fabric? Now all you have to do is add a material attribute to the clothing class, and all the children classes automatically inherit the new attribute. Your code becomes more efficient to write and maintain. Next, I'll go through the Python syntax for inheritance. Then you'll add inheritance to the Gaussian class.
When your model produces the quality and accuracy you're looking for, you can begin to use your model to solve the original problem. Once you have trained your model and evaluated its effectiveness, you're ready to generate predictions from real, unseen data in the field. In machine learning, this process is often called inference. Keep in mind that you will always be monitoring to make sure your model is producing the kinds of results that you're expecting. As we mentioned before, there may be times where you reinvestigate the data or even change the model type used for training.
Welcome to the AWS DeepRacer console. Let's start on the AWS DeepRacer League page, where thousands of racers across the world meet to compete with their reinforcement learning model every month. The AWS DeepRacer League structure splits the current virtual circuit monthly leaderboard into two skill-based divisions, Pro and Open. Each division offers its own racing formats and opportunities for prizes to maintain a high level of overall competitiveness. All racers begin their machine learning journey in the Open division. Open division racers compete in the time trial format and receive monthly digital rewards for participation. Racers who have earned a top 10% time trial results from the previous month race in the Pro division. Racers in the Pro division will earn bigger rewards and can compete in the monthly final for qualifying seats in the yearly AWS reInvent Championship. Pro division racers compete in more complex racing formats such as head-to-head or object avoidance, which requires stereo camera or LiDAR sensor configurations. Live monthly races winners of the Pro division finale automatically secure a spot in the Championship Cup and a trip to AWS reInvent to compete for $10,000 in AWS credits, as well as an F1 experience or a $20,000 value machine learning education sponsorship. On the left side of the navigation, you also see the community races. Community races are races organized by AWS DeepRacer users who are not officially sponsored by AWS. You can create your own community race and invite your colleagues, classmates, or friends by sharing a race invitation link. Now let's go to the garage section. In the garage, you can create and configure sensors and customize your agents. You can see the list of cars in your garage. Here I have a U car, a cool van, a newbie as cars in my garage, which are a mix of sensor configurations and vehicle skins I've earned through participation at events. Now let's build a new vehicle. First, choose a name for your new car. Let's say Udacity car. Then select one of the vehicle shell to customize. I'll take the van shell I earned by participating in the March virtual circuit race, and then I'll select the color between white and DeepRacer purple. Here I'll select the purple. You can move the car, the 3D model, so that you can see how it looks from different angles. Once you're done and happy, hit next. Now it's time to choose the sensor configuration for your agent. A single camera is good for racing without any objects or cars on the track. You'll want to use stereo camera to race in head-to-head and object avoidance formats, as it gives you depth information, like your two eyes give you a sense of depth. LiDAR sensor is a light detection and ranging sensor. It scans its environment to inform you of the presence of objects or cars. For your first model, we'll go simple and select a single camera sensor configuration. Hit next whenever you're ready. Finally, you'll select the action space, which is the list of actions your agent can take. First, select the type. A discrete action space represents all of the agent's possible actions for each state in a finite set. A continuous action space allows the agent to select an action from a range of values for each state. Choose the maximum steering angle you want to apply to your car when it turns, then the max speed for your car to drive at on the track. We recommend to start with the default settings for now. Let's go with the discrete action space. You can review the list of all actions your car will be able to take in the action list below. It looks like you're done with your car. Hit done.
Here, you can see the clothing class that I was just talking about. It looks a lot like the shirt and pants class that you coded at the beginning of the lesson. The shirt and pants classes inherit from the clothing class. That's why the class declaration of shirt and pants have clothing in parentheses. This tells Python that the shirt class and pants class should inherit all of the attributes and functions of the clothing class. Looking inside the shirts init method, there's this new syntax where clothing.init gets called. All that means is that a shirt object initializes itself using the clothing's init method. Then you can add any extra attributes like the long or short attribute in the shirt class or waist in the pants class. You could also extend the shirt or pants class by adding more methods. To give an example, I could add a double price method just to the shirt class. You could also override any of the clothing methods. For example, the pants class is overriding the calculate discount method. Remember, one of the main benefits of inheritance is that you can add attributes and methods to the clothing class, and then both the shirt and pants class will have those attributes and methods as well. Study all of this code to get used to the syntax of inheritance.
As a prerequisite to this course, you should have already learned how to use Git for version control. If, however, you need a refresher, check out the course linked in the extracurriculars. To familiarize yourself with how you may use version control at work, we'll first take a look at an example scenario where you are a data scientist using Git at work. We'll practice the commands you'd use in these type of scenarios, and then we'll go over some of the unique challenges and techniques for versioning data science work.
You have learned about the tasks of machine learning workflow. Now let's see what this actually looks like in real life. We are going to look at 3 case studies showing 3 types of machine learning tasks. Supervised learning task, where we try to predict housing prices for homes in your neighborhood based on lot size and number of bedrooms. And unsupervised learning task, where we try to use machine learning to find interesting collections of books in a book dataset based on descriptive words in the book description. And finally, we will see a 3rd case study where we use a more model called a deep neural network to try to detect chemical spills in a lab from video and images. While neural networks are beyond the scope of this lesson, we felt it's worthwhile to touch on how they work.
Now, I'll walk you through how to train your first model. First, on the AWS DeepRacer homepage, choose Your Models from the main navigation pane to open Your Models page. On the Your Models page, choose Create Model. On the Create Model page, under Training Details, enter your model name. Let's call it Udacity model. Add a description. This is my first model. Then under Environment Simulation, choose a track as a virtual environment to train your AWS DeepRacer agent. Let's select the Lars loop and hit Next when ready. On the Create Model page, under Race Type, choose one of the training types. For your first run, choose Time Trial. The agent with the default sensor configuration is good for this type of racing without modifications. Under Training Algorithms and Hyperparameters, use the default hyperparameter values as is. Later on, to improve training performance, you can expand hyperparameters and try tuning them. Under Agent, you can choose the original DeepRacer or any of the cars that you have in your garage for your first model. When ready, hit Next. Now, under Reward Function, use the default reward function example as is for your first model. However, you can select from other examples for time trial and object avoidance and head-to-head. For this, you'll want to use code and then validate this code. Later on, you can choose other reward function examples to select another example of reward function and then choose to accept the selected reward function. As you grow in skills, you can customize or create your own reward function. Under Stop Conditions, set the training time for your model training. To get you started, we recommend training your model for about 2 hours and see how it performs. So I'll enter 120 minutes. Once you're done, choose Create Model to start creating the model and provisioning the training job instance. After the submission, watch your training job begin, initializing, and then run. The initialization process takes about 6 minutes to change status from initializing to in progress. After the submission, watch your training job being initialized and run. Watch the reward graph and simulation video stream to observe the progress of your training job. In green, you'll see the average reward the agent earns during one training iteration. The average is calculated by averaging the reward earned across all episodes in the training iteration. In blue is the average percentage of the track completed by the agent in all training episodes in the current training iteration. And in red, that is the average percentage of the track completed by the agent in all episodes run during the evaluation period, while SageMaker is updating the model using the current iteration of your model. The training job is running on the AWS cloud, so you don't need to keep AWS DeepRacer console open during the training time. However, you can come back anytime to the console to check on your model at any point while the job is in progress to see how your car performs on the track.
To reinforce how inheritance works, I've added an example to the Gaussian class code. I've written a new Python class called distribution. This class is going to be the parent class of both the Gaussian class and the binomial class that you are going to code at the end of the lesson. A lot of the code should look familiar. The init function was the same as the Gaussian init. I've simplified the read data file function so that it only reads in a data set, whereas before this function also calculated the mean and standard deviation of the data. The Gaussian class code has changed slightly. Now the Gaussian class inherits from the distribution class. The init function uses the distribution's init function. Scrolling down, the read data file method is still in the Gaussian class. This is because I wanted to override the read data file method from the distribution class in order to calculate the mean and standard deviation. Even though the code looks a little bit different than before, the Gaussian class works exactly the same way as it did before. It might seem like the changes in the code are superficial, and I'd agree with that. I mostly wanted to introduce inheritance so that you could recognize the syntax. Near the end of the lesson, we're going to look at the source code for scikit-learn. A package like scikit-learn contains many classes that use inheritance. You'll have an easier time understanding the syntax now that you've seen how inheritance works. I've provided this distribution and Gaussian code for you in the next section so that you can play around with it. We're getting close to the end of the lesson. The next step is to modularize all of this code into separate Python files. Then you'll see how to make a Python package. And the last steps will include extending the code to include a binomial distribution and uploading the code to PyPy. So let's start by modularizing this code.
Imagine you're part of a data science team that's responsible for building a company's recommendation engine. You're sitting at your desk working on a feature that incorporates demographic data like age, gender, and relationship status to improve recommendations to users. You're midway through this implementation when your boss comes over to notify you that the business intelligence team predicts that a user's friend groups would produce the best recommendations in the short term and wants you to prioritize this immediately. Looking at the recommendation engine code you have on your screen, you can see there's a bunch of unfinished, non-working code that you've added while working on the demographic feature. Running this code right now would break. If you want to get started on this new friend groups feature now, you'd have to undo all of this work, maybe by editing back lines you've modified and commenting out lines of code you added. This would be a very messy and risky route. Or, say you're using a version control system like Git. You can simply commit your changes and create another branch for this new feature. Here's what I mean. Your company has a Git repository for its recommendation engine and has a master branch, which holds the code used in production, and the develop branch, which holds the latest stable version of code with changes for the next release. You have a local version of this repository on your laptop, and to get the latest stable version, you pull from the develop branch. When you start working on this demographic feature, you create a new branch for this called demographic and start working on your code in this branch. However, in the middle of your work, you need to work on another feature. So you commit your changes on this demographic branch and switch back to the develop branch. From the stable develop branch, you create another branch for a new feature called friend groups. After you finish your work on the friend groups branch, you commit your changes, switch back to the development branch, merge it with the friend groups branch, and push this to the remote repository's develop branch. Now, you can switch back to the demographic branch to continue your progress on that feature. As you can see here, proper use of Git commits and branches can help you work on multiple features at once and switch between them with ease.
We will start with one of the most common examples in machine learning coursework, house price prediction. You want to predict the value of homes in your neighborhood. You know that real estate appraisers use many details to predict value, such as the number of rooms and the house size. Therefore, even if you don't understand the relationship fully, you believe a relationship exists between these observable details and the house price. You choose to use machine learning to discover this relationship based on the data you have access to. Because you think you can find either the actual prices for homes recently sold in your neighborhood or generate accurate estimates for others by asking a real estate appraiser, you are working with a supervised learning task. Because you're trying to predict some continuous numeric value, you recognize this as a regression machine learning task. First, you do data collection. You collect numerous examples of houses which sold in your neighborhood within the past year and pay a real estate appraiser to appraise the house whose selling price is not known. Next, you do data exploration. You notice that all of your data are numbers, which is great, since most machine learning models operate on sequences of numbers. Finally, you do data cleaning. You look for things in the dataset such as missing information, or maybe an outlier that you don't really care about in your problem, such as a mansion with 10 rooms. You know techniques exist to handle these cases, but for now, you choose to just remove these examples from your dataset. You might also plot house value against each of your input variables and observe that when either a lot size or room count increases, how the house value changes. You split 80% of your dataset randomly into a training dataset and 20% into a test dataset. Okay, you're ready to try training a model. You do model selection. After exploring the data, you observe that the relationships between your input variables and label are pretty straightforward. When lot size increases, house value increases. You think this relationship is simple enough that you select a linear model to represent it. A linear model across a single input variable can be easily thought of as a line. It becomes a plane for two variables, and then a hyperplane in more than two variables. But thinking of it as a line with a constant slope will get us far enough in this example that we'll show it depicted here. To do the actual model training, you load your data in Python arrays and use a common Python library toolkit for training classical models. One of the most commonly used evaluation metrics in regression scenario is called RMS, or root mean square. The math is beyond the scope of this lesson, but RMS can be thought of roughly as an average error across your dataset. So you want this value to be low. In the chart shown here, you can imagine we want the line to be close to the data inputs. You compute the root mean square between your model's prediction of a data point and the true home value found in your dataset. You're still new to machine learning, so you're not sure how to interpret these results. You know that having an improved model will probably have a better RMS, but you're not confident if the specific value you have computed is good or bad. As a sanity check, you manually count how many predictions were off by some thresholds, 50,000 let's say, and determine that your model is pretty accurate within this range. You now use this model to predict the house value for other houses on the market. As you see in this example, we can pass any room count and lot size we want to predict a new home value.
Once your model is trained, you can decide to evaluate how well it performs on the track. To do so, navigate to your models, select the model you want to evaluate to start a new evaluation. Here, I'll select a previously trained model called AWS DeepRacer because my Udacity model is still in training for about 2 hours. You can see that the training for this AWS DeepRacer model is completed. I will want to go into evaluation, so I'll start evaluation. Because I want my model to perform the best, I will select a track that is similar or the same as the one I trained the model on. Once I've selected the track I want to evaluate the performance of my model on, I will choose a racing type. Here we'll stick to time trial because remember, I trained my model in time trial. Whenever I'm ready, hit Start Evaluation. And the evaluation will start in the console. During evaluation, the car will go around the track. You'll see on the right side the performance. Here, my model did not perform very well with 19% of track completion rate, 17%. I still have some work to do on my model. Now that you have your first model, it's time to compete and see how you compare to others. To do so, navigate to the virtual circuit page and enter the race. Choose the model you wish to submit, then enter the race. Here you will select Open Division, and I have raced already, but if you're a new racer, you will here choose a model, let's say AWS DeepRacer, and enter the race. Here you'll have a notification telling you that your model was submitted to the April qualifier time trial race, and that the results should be available here on the leaderboard in about 10 minutes. Now that you're ready to race, let's create a cool profile avatar for you. Navigate to your racer profile, select Edit, and here you can define your avatar to represent you on the DeepRacer console. You can select a different skin tone, how your haircut will look. Let's say this is my new avatar. I'll have platinum hair. new glasses, surprised eyes, a grin, and I can even change my country. Let's pick Iceland and hit save. Your new Racer profile is set and your pic will appear on your console. Others will be able to view your profile avatar if you rank number 1 in the race.
After working on this recommendation feature for a while, you've created a model to produce recommendations based on friend groups. The model is scoring pretty well on your validation set, but you remember it did even better just a few hours ago. You've been experimenting with tweaks to this model, and you're not sure what combination of parameters and tweaks were in place when your model scored the highest. Luckily, you've been including a message with each commit noting what you did, as well as the training and cross-validation scores for each commit. Instead of spending a bunch of time trying to retrace your steps from memory, or testing a bunch of tweaks again to try and get the same score, you can check your commit history, seeing messages of the changes you made and how well it performed. The model at this commit seemed to be scoring the highest, so you decide to take a look. After inspecting your code, you realize what modifications made this perform well and use those for your model. Now, you're pretty confident merging this back to the develop branch and pushing the updated recommendation engine.
Let's explore a second example. You do editorial work for a book recommendation company, and you want to write an article on the largest book trends for the year. You are aware of trends described as macrogenres. For example, teen vampire romance novels. You have high confidence that other macrogenres exist, and you believe that words and phrases used in the back of the book description might provide some guidance on which macrogenre a book belongs to. You think you can use machine learning to explore whether books can be grouped together in this way. You anticipate that books with similar content use similar words on the back of the book. You think that macrogenres might be represented as groups of books whose description use very similar words. You would define the problem as, let's find the clusters of similar books based on presence of certain words. Earlier in this lesson, we discussed unsupervised learning. Remember, this is especially useful if our data is not labeled. You decide to use an unsupervised machine learning called clustering approach to explore this proposed structure. Data collection. You collect back of book text for 800 romance books published in the current year. Because you don't think capitalization and verb tense matter for the structure you propose, you remove capitals and convert all verbs to the same tense. For this, you can even use Python library built for processing human language. You also remove punctuation and words you don't think have useful meaning like a and the. Data vectorization is a process which turns the words into numbers. You transform this bag of book text into what is called a bag of words representation, which is understandable by machine learning models. How bag of word works is beyond the scope of this course, but in this image here, you can see it just transforms the text into a sequence of numbers. Through some internet searching, you determine the clustering model called K-means is a good first choice because it's simple and general purpose. The K in K-means defines how many clusters the model will find. You don't know how many macrogenres exist, so you run model training for multiple values of K, let's say 2, 3, all the way up to 40, and plan on choosing the best one during model evaluation. What does this look like? In this example, you can see K equal 2 clusters, and here is K equal 3 clusters. When evaluating machine learning models, there are many options for the statistical metrics you can use to help determine how effective your model is. Most of these metrics are beyond the scope of this lesson, but as you start to use machine learning, you will learn to research and identify these metrics to help you evaluate your model most effectively. In this case, silhouette coefficient will serve us well. Alright, we are back to our example. Silhouette coefficient is a common metric for determining how well your data was clustered. You plot the silhouette coefficient for each model you trained in the previous step and observe some sudden point of diminishing return as you increase k. So it seems as if you have identified k equal 19 clusters here. Through quick spot checking, you see one cluster within this model contains a large collection of books which you categorize as paranormal teen romance. Because this is a known trend in your industry in the present year, you feel somewhat confident in your machine learning approach. You don't know if every cluster is going to be as cohesive as this, but you decide to use this model to see if you can find anything interesting to write an article about. You find a surprisingly large cluster of books, cluster number 7, shown here where the people are in a long-distance relationship. Mission accomplished. You see a few other self-consistent clusters and feel you now have enough useful data to begin writing an article on. Maybe you can title the article Unexpected Model Romance Microgenres.
Hi, welcome to Generative AI section. In this section, you will learn about generative AI. We'll explore a selection of popular generative AI techniques and how they work. Then we will get hands-on with AWS DeepComposer to experiment with generative AI. We hope this section can give you a general understanding of generative AI and motivate you to dive deeper and practice more.
In this section, we will first learn about generative AI and 3 commonly used generative AI models. Then we will introduce AWS DeepComposer and how it has been designed to make the learning of machine learning, specifically generative AI, more interesting. We will then introduce some of the most popular generative AI models in more detail for you to dive deeper. Let's review the different types of machine learning models one more time. We talked about supervised learning, unsupervised learning, and reinforcement learning. Focusing on unsupervised learning for this section, we have learned that in unsupervised learning, there are no labels for the training data, and the algorithm tries to understand the underlying patterns or distribution that governs the data. Related to this section, generative AI models are mostly unsupervised. Another way to classify models is to organize them into discriminative or generative techniques. Let us consider a cat-dog detector. In discriminative technique, the model learns to classify, for example, cat versus dog, or detect, for example, face detection. In this example, cat image is fed as an input into a cat-dog detector, which has learned to differentiate between images of cats and dogs. As expected, the model is able to predict that the image is indeed a cat and not a dog. In contrast to discriminative technique that learns to classify, generative AI techniques are mostly involved in creating new data by using the pattern learned during training to generate new data. Let us look at an example of a generative model that is trained on cat images and has learned to create a brand new image of the cat. When the model is asked to generate a new model during inference, it creates a brand new image of the cat. It's good to note the limitation here that our generative model can only create new things in the style of the data it has been trained on.
Generative AI opens the door to an entire world of possibilities for human and AI to collaborate, with practical applications emerging across industries, from turning sketches into images for accelerated product development to improving computer-aided design of complex objects. There are currently techniques that use generative AI algorithms to construct detailed 3D crown models from images of other teeth. This results in a crown that has similar anatomical detail
to the original teeth they are replacing. In the next section, we will learn basics of the algorithms in generative AI. But before we dive deep, let's have an overview of these algorithms. Three popular types of generative models are generative adversarial networks, short form GANs, general autoregressive models, and transformer-based models. You will later learn how these methods can be implemented in the context of music with AWS DeepComposer. But before that, what are these models? GANs, or Generative Adversarial Network, is a format for a machine learning model which involves pitting two neural networks against each other to generate new content. One network is called the generator network, which is responsible for producing new data. The discriminator network then classifies the new data as either real or fake and gives feedback to the generator to adjust. GANs have been shown to achieve impressively realistic computer-generated photos and are being explored within other domains as well. Later, we will take a look at GANs within AWS DeepComposer. Autoregressive models are used to study systems which evolve over time, and they rely on previous time series data to generate accurate new data. It's a useful way of looking at many systems, from weather prediction to stock prediction. Later, we will review ARCNN, an example implementation of this type of model in the AWS DeepComposer console. Transformer-based models are most often used to study data that is sequential in nature. For example, think about a pixel which makes up an image. You cannot randomly rearrange and still make sense of that image. This is because the sequence of pixels matters. Since natural language is sequential in nature, transformer-based methods can be used to model natural language. Although with AWS DeepComposer you can learn transformer models and get hands-on with them, it's beyond the scope of this course, so we won't talk about them in detail.
From this point in the lesson, you're going to use a Linux environment with Python scripts rather than a Jupyter notebook. Jupyter notebooks are great for data science, but they're not necessarily the best tool for writing modular software. In the next section, you'll see a classroom workspace like this one containing the code I'm about to show you. On the left-hand side, you'll see a list of directories that you can access. Each section in the rest of the lesson has its own folder. This part of the lesson is discussing the modularized code folder. Let's talk about how to modularize the distribution and Gaussian classes with which you've just been working. In Python, a module is a single Python file that contains a collection of functions, classes, and/or global variables. They're called modules because, well, they're modular, meaning that you can reuse these files in different applications. A package is essentially a collection of modules placed into a directory. If I double-click the folder containing the modularized code, there are 3 files, but these 2 are the most important, GaussianDistribution.py and GeneralDistribution.py. These files contain the same code from the section on inheritance. This folder isn't quite officially a package yet, but putting these files into the same folder is the first step to making a package. Opening the GeneralDistribution.py file, the distribution class code is the same as it was in the Jupyter Notebook. Opening the GaussianDistribution.py file, you can see that it contains the Gaussian class. The code here is almost the same as the code from the Jupyter Notebook. However, notice that the Gaussian distribution file imports the distribution class. This line says, go into the GeneralDistribution.py file and give me access to the distribution class. I want to point out that you can also use the same syntax to import a function from a module, not just a class. But for this lesson, we are focusing on object-oriented programming, so I coded everything inside a class. How can I actually use this Gaussian distribution module in a Python application? You can see an example in the examplecode.py file. This file imports the Gaussian class and then instantiates a Gaussian object. Note as well that my example code file and the Gaussian distribution.py file are in the same directory. You'll see later in the lesson that packages and applications do not need to be in the same directory as long as Python knows where to look for a package. Next, I'm going to open a terminal window and run the example code.py file. If you're not familiar with using the terminal, don't worry too much. Each section of this lesson comes with an instruction file discussing how to run commands in the terminal. Typing python 2_modularized_code/example_code.py and hitting enter runs the Python module example code.py. This code prints out the mean of the instantiated Gaussian distribution object, which is 22. In the next section, you'll have the chance to look at this code in more detail. As you might have done before, you install Python packages using pip install. For example, if you want to install the scikit-learn package, you go into a terminal and type pip install scikit-learn. This pip install command downloads packages from an online repository called PyPy. In this case, scikit-learn is already installed, so it's just letting you know. In the remaining parts of this lesson, you're going to set up a Python package and then upload the package to PyPy. The first step is to get the package ready so that it can be pip installed locally on your computer. I'm going to show you how to set up your files so that they can be pip installed. On the left-hand side of the screen, you can see I'm in a directory containing a folder called distributions and a file called setup.py. Let's talk about the distributions folder first. Double-clicking, this folder contains the Gaussian and general distribution classes that you've already been working with. The difference is that this folder is now officially a Python package because the folder contains an init file. A package needs an init file. There's nothing new or different about the Gaussian and general distribution files except for one line. Opening Gaussian distributions.py, you can see the third line where I import the distribution class from the general distribution.py file. There's a dot in front of general distribution. This dot is required in Python 3, but if you're working in Python 2, you shouldn't need it. The init Python file, on the other hand, is new. The init file is telling Python that this folder contains a package. A package always needs to have an init file, even if the file is completely empty. The code inside the init file gets run whenever you import a package inside a Python program. In this case, the init file is importing the Gaussian class from the Gaussian distribution module. The reason I added this line is because I want to be able to import the Gaussian class directly, writing from distributions import Gaussian. You'll see what I mean in a bit. If I didn't include any code in the init file, the package would still work, but any program that uses the package would have to import the Gaussian class more indirectly with the line from distributions.Gaussian distribution import Gaussian. It's like I'm making a shortcut for importing the Gaussian class directly. Going back up one level in the directory, there's a setup.py file at the same level as the distributions folder. This file is necessary for pip installing. Pip will automatically look for this file. Opening this file, you can see the setup file contains information or metadata about the package, like the package name, version, description, etc. Okay, let's install the package. To install the package, go into a terminal and make sure you're in the directory with the setup.py file. In this case, I'm going to have to change directories and type Python package example. Okay, now I'm in the directory containing the distributions package and the setup.py file. In the terminal, type pip install dot and then hit enter. The dot tells pip to look for the setup file in the current folder. That's it. The Python package is installed. Now I can use the package in my Python code like so. I'm going to open a new terminal. Notice that I'm no longer in the Python package example folder, and it doesn't matter because we've already installed the package. So I'm going to type Python to start the Python interpreter, and then I'm going to import the Gaussian class, saying from distributions import Gaussian and hitting enter. Okay, now I have access to the Gaussian class. So I can write something like Gaussian 1 equals Gaussian class and initialize it with a mean of 10 and a standard deviation of 5. Hit enter. And now look, I can use the Gaussian class just like we were using it before. And you have access to all the methods as well. So you might ask yourself, where exactly did the package get installed to? The answer is wherever pip installs packages on your system. If you're still in a Python interpreter and type import package, like import distributions, you can then type distributions dot underscore underscore file underscore underscore, hit enter, and that'll tell you where the package is installed. That's all it takes to create and install a Python package locally. In the last part of the course, you're going to expand this package, creating a binomial distribution class. And then you can upload the package to PyPy so that anybody can download and install your package. If you decide to install this package on your local computer, you might want to create something called a virtual environment first. A virtual environment is like a silo for installing Python packages. That way, you won't be messing around with your computer's default Python installation. I'll put instructions on the next page for setting up a virtual environment.
While you were working on these changes, your coworker, Andrew, has been working on improvements to the documentation of the same recommendation engine on a different branch called documentation. Andrew commits his changes to the documentation branch, switches to the development branch, and pulls down the latest changes from the remote repository on this branch, which includes the change I previously merged for the friend groups feature. Then Andrew merges his documentation branch to the develop branch on his local repository, and then pushes his changes up to update the develop branch on the remote repository. After the team reviewed both of your work, they merged the updates from the develop branch to the master branch. Now they push the changes to the master branch on the remote repository. These changes are now in production. Using branches, commit messages, and merging demonstrate just a few ways version control can be used in data science on a team. But the process will vary based on your team.
Let's review example number 3. In the past examples, we use classical methods like linear models and k-means to solve machine learning tasks. In this example, we will see a more modern model type. You run a company which offers a specialized on-site janitorial services. One of your clients, an industrial chemical plant, requires fast response for spills and other health hazards. You realize you should be able to mobilize your janitorial team faster if you could detect the spills from the plant surveillance system. You investigate using machine learning to perform this automatic detection. You recognize you can represent this task as a supervised classification task. Your goal will be to predict if each image belongs to a contains a spill class or it does not contain a spill class. Since you run the janitorial service, it's pretty easy for you to stage safe for spills. You quickly build a collection of images that contain both the spills and non-spills in multiple lighting conditions and environments. Exploring and cleaning your dataset is pretty straightforward. You quickly flip through all photos to ensure the spill is clearly in shot. You split the images into a training dataset and test dataset. The surveillance system produces only grayscale images. You convert the image to numeric data so the model can process the data. To demonstrate this, in this example of a dark liquid spill, you can see each pixel in the image on the left can be represented in the image on the right by a number between 0 and 1, 0 being completely black and 1 being completely white. Traditionally, to solve this problem, a human would have to manually label the features in the image. For example, locations of prominent edges and corners in the image, and then train a model on these features. Today, deep neural networks are the most commonly used tool for the problems like this. These deep neural networks can learn the features in an image as long as they have been labeled. CNN, or convolutional neural network, which is a common deep learning model for processing image, is a good model choice for this task. These neural networks are made up of many different types of layers. These layers are required for neural networks to train successfully. The details of neural networks are beyond the scope of this lesson, but we wanted to at least introduce the idea. So we will keep things high level for now. You begin training to solve your classification task here. As we saw in our last example, there are also many options for the statistical metrics you can use to help determine how effective your neural network model is. As you further explore machine learning, you will learn to research and identify these metrics and learn which one help you evaluate your model most effectively. As we will see here, precision and recall will be effective in this example. You stop and realize that accuracy might not be the best evaluation mechanism. Defined as percentage of correct predictions, you realize the model will see the noticeable class almost all the time. So any model that just predicts noticeable most of the time will be pretty accurate. What you really care is an evaluation mechanism that rarely misses a real spell. After doing some internet search, you realize this is a common problem. You augment your accuracy evaluation mechanism with the evaluation metrics precision and recall. You can think of precision as answering the question, of all predictions of a spill, how many were right? Or in this example, how often will I be sending a janitor to clean an actual spill? You can think of recall as answering the question, of all actual spills, how many did we detect? Or in this example, how many of the spills did my system catch? You also realize your stage of spills might not have been sufficiently realistic, and you really want to have a good sense of how well your model will do when you use it. You spend an hour searching through historical records of the surveillance system and find a few cases of real spills. You evaluate your model against this dataset and confirm that it is performing satisfactorily. Confident in these results, you deploy this model on a system that enables you to run machine learning workloads on surveillance systems. You implement a simple paging system and begin transitioning your team to respond to these pages in addition to their typical routines. We have heard from developers again and again that learning new machine learning techniques, especially cutting-edge ones, is difficult due to the fast-moving academic literature or dry technical content. This is why we created AWS DeepComposer, so that we get you started with machine learning and generative AI in the context of music. This is why we created AWS DeepComposer, so you can get started with machine learning and generative AI in the context of music. It's fun and hands-on. What is AWS DeepComposer? AWS DeepComposer gives you a creative and easy way to get started with machine learning, specifically generative AI, using music. Regardless of your background in machine learning and music, you can get hands-on with AWS DeepComposer and learn the fundamentals of generative AI. AWS DeepComposer is an AWS service offering technical content as well as a music studio for you to learn generative AI by creating music. AWS DeepComposer also offers a keyboard device to make your music creation experience easier. But you don't need the device or knowledge in music to learn generative AI with AWS DeepComposer. To get us started, you can go to AWS Music Studio, record an input track, import your own MIDI file, or use a sample track. Then you can experiment with any of the generative AI models AWS DeepComposer offers. With GANs, you can add accompaniments to your melody. With ARCNN, you can enhance your melody to sound more like Bach music. And with Transformer, you can extend your melody by up to 30 seconds and create your very own piece of music. In this lesson, we will dive into GANs and ARCNN using AWS DeepComposer.
Great job finishing part 1 of software engineering practices. You learned valuable skills that will help you in all of your future programming work as a data scientist. Being able to write code that's clean, modular, and efficient makes you a stronger developer and allows you to easily reuse and share your code. And using effective documentation and version control are such important practices in industry that will really help you in future projects. Congratulations again on completing this lesson.
Congratulations on completing this lesson. We went through a lot of information to give you a foundational understanding of machine learning. Hopefully you now have a better sense of what machine learning is. Let's look back and see what we covered.
We discussed machine learning as a complex subject area to understand what machine learning is and what are the common components involved in machine learning projects. We also introduced you to some most common terms and ideas that are used in machine learning. We discussed how machine learning involves using trained models to generate predictions and detect patterns from data. And we looked a bit behind the scenes to break down the different steps involved in machine learning. In this section, we took you through a couple of real-world examples which use machine learning in different ways to solve real-world problems. In this demo, I want to walk you through AWS DeepComposer console and show you what AWS DeepComposer offers. First, go to aws.amazon.com/deepcomposer. That takes you to this page. In this page, you will find more information about what AWS DeepComposer offers. You can choose Buy Now to purchase the keyboard to improve the music creation experience. The keyboard is currently offered at a special price for a limited time. In this page, you will find all the information you need to use AWS DeepComposer. DeepComposer consists of a keyboard, console, and competitions. In order to learn how to use the console, this page provides you a step-by-step guideline on how to use AWS DeepComposer. Once you're ready, choose Start Composing. After signing in, you are now in AWS DeepComposer console. You can choose to review the fundamentals of machine learning, generative AI, and AWS DeepComposer by choosing this orange button, which reads, Start Learning Generative AI. In 7 summarized chapters, you will learn what happens behind the scene of AWS DeepComposer and all you need to know to use AWS DeepComposer to create music. Let's go back to the console. We are back in AWS DeepComposer console. You can find all its offering in this navigation pane on the left side. Music Studio is where all the magic happens. Regardless of your background in music or machine learning, you can generate your very own piece of music in 30 seconds or less by collaborating with AI. There is another demo in this course walking you through the experience of generating music using AWS DeepComposer Music Studio. If you want to train your own model, this is where you go. You choose Create a Model. You will find all the models you have previously trained in this list, or you can check out the sample models we have provided for you. To find all the compositions you created, this is the list you need to check. You will find all the compositions here. You can take actions such as sharing on SoundCloud, downloading it, or deleting it if you want. The next option are Chartbusters. Chartbuster is a monthly competition, now continuing until November 2021, in which you can create compositions to top the charts and win prizes. We have 2 competitions for you. Basic challenge called Melody Go Round. You can use any input track and ML technique to create a melody that's uniquely you. For the advanced challenge called Melody Harvest, You can train a model using your own music in Amazon SageMaker. Make sure you check out the past challenge winners' compositions here. Last but not least are learning capsules. Learning capsules are bite-sized learning modules for those of you who want to dive deeper into what we reviewed in this course. For example, you can check out Introduction to GANs, Introduction to ARCNN. You can deep dive into training an ARCNN model. You can review a history of sequential modeling, or you can learn more about the transformer technique. We didn't cover this technique much in this course, so I highly recommend you check this out. Feel free to explore the AWS DeepComposer console yourself. I hope you enjoyed the experience.
I want to show you how virtual environments work in Python. Unfortunately, you might run into different issues depending on your operating system and Python installation. The Classroom workspace uses an Ubuntu Linux operating system and a special Python installation known as Anaconda. In this particular case, there are some issues with the virtual environment package, and a quick fix is to run conda update Python and then hit enter. Running this command takes a while, so I've already done it before recording. If you're not using Ubuntu or Anaconda, you shouldn't need to run this command first. If everything is working correctly and you're using Python 3, the virtual environment package should already be installed. You can type python-m venv and then your virtual environment name and hit enter in the terminal. venv_name is the name you want to give to your virtual environment. You can name it anything you want. If you go over here into the workspace area, you'll see there's a new folder called venv_name. Inside of that is a Python installation. Now you can type source venv_name/bin/activate, hit enter, and you'll see that the virtual environment is now activated. So anything you install now will get installed into the virtual environment instead of your default Python installation. You'll notice that the command line now shows in parentheses the virtual environment name at the beginning of the line, indicating that you're using that virtual environment. Now I'm going to change to the directory where I have my Python package and setup file, and then I say pip install dot like before. Okay, and now I've installed the distributions package into the virtual environment instead of the default Python environment that's installed in the computer. That's really it for virtual environments. The benefit is that you can experiment with Python without affecting your default Python installation. You can always just delete the virtual environment folder from your computer, and there shouldn't be really any consequences in terms of your default Python installation. Now it's your turn. You've practiced the basics of object-oriented programming in Python. Time to show off your skills. In the next section, you'll find the code for the distribution package, but there's also a new file containing a binomial class. Your task is to write the code for the binomial class methods. You'll also have to use all the skills seen so far, including inheritance and writing magic methods. You'll need to code an initialization method, calculate the mean and standard deviation, and fill out other methods similar to the ones in the Gaussian class. Once you've finished coding the binomial class, I've got a few more fun activities in store, including looking at the source code of scikit-learn and instructions for how to put your package on PyPy. Okay, time to write some code.
As we learned before, GANs are one of the most popular generative AI techniques that pits two networks against each other to generate new creative content. The best way we have found to explain this is to use the metaphor of an orchestra and conductor. An orchestra doesn't create amazing music the first time they get together. They have a conductor who both judges their output and coaches them to improve. So an orchestra trains, practices, and tries to generate polished music. And then the conductor works with them as both a judge and a coach. The conductor is both judging the quality of the output where the right notes played with the right tempo, and at the same time providing feedback and coaching to the orchestra, specifically to achieve a style that the orchestra conductor knows. In generative adversarial networks, the generator is responsible for creating new data, just like how orchestra creates new music. And the discriminator works like the conductor who both judges the output and provides feedback to improve the performance. Note that discriminator here performs two separate actions, classifies the data output and provides feedback to the musician. Both parts are essential for a discriminator to function properly. Just like how the orchestra and the conductor need to practice to create beautiful music, generator and discriminator also need to practice together to generate data that resembles the real data. In machine learning, we call this practice a training process. Now let's look at the training process within the context of AWS DeepComposer. Given a single piano track, we can use GANs to add accompaniments track to different genres. As we saw before, the idea of GANs is that you have two networks, the generator and discriminator, that constantly compete with each other to create new realistic data. Here, music. The generator, as the name suggests, tries to create new music. Here, accompaniment tracks. The discriminator critiques how realistic the generated music is. Using the feedback from the discriminator, the generator tries to improve the music it created. With time, the generator gets better at generating music and is able to fool the discriminator. So periodically, discriminator is also retrained using the new generated data so that it becomes even better at discerning generated music from real. Now let us hear some samples from AWS DeepComposer. The first sample is the input melody of Twinkle Twinkle Little Star with sample piano notes. The second sample is the output created by the GAN model. Taking a single track piano input, the model has created a multi-track output by adding accompaniments in the rock genre. Let's listen to the output composition. Beside music, there are other practical uses of GANs. For example, scientists have recently used generative models to create new drug-like small molecules targeting novel viral proteins. This could potentially help with faster drug design and discovery. Humans and AI can collaborate to create original artwork never seen before. Humans can bring in their unique creative knowledge, while generative models can learn from a vast set of training datasets that may not be known to a single person. Cancer detection often needs a huge dataset that is not typically available. Generative models such as GANs can be used to generate synthetic images of cancer and non-cancer cells to augment the training dataset and produce more accurate detection.
Before you get started writing code, here's a quick overview of the binomial class exercise. The exercise is contained inside this 4A binomial package folder. Inside this folder are quite a few files and a distributions directory. Out of all these files, there are two that you're going to need to modify. First is the init Python file inside the distributions directory here. Currently, the init file only imports the Gaussian class. You'll first need to modify this file to also import the binomial class. Going back, take a look at the binomial distribution file. You'll see that I've put in a bunch of to-do sections to help guide you along. Make sure to read the to-dos so that you understand what the code should look like. Each method also contains a doc string explaining the expected inputs and outputs. You'll see as well that I've included a file called tests.py. This file contains unit tests that you can run to help you determine if your code is working properly. Here's how to use this workspace. First, you'll need to open a terminal and go into the package directory with the command cd 4a binomial package. Then you can type pip install dot, which will install the distributions package. The unit tests are in the test.py file. You can run the unit tests by typing python test.py. As you modify your code, you can run the test.py file to see if your code is working. In this case, it tells me that from distributions import binomial in the test file doesn't work. That's because I never put it in the init file inside the package. As you modify your code, you can run the test.py file to see if your code is working. However, whenever you update the package code, you need to reinstall the package. Otherwise, Python won't be able to see the changes you've made. You can reinstall the package by going to the terminal, again, making sure you're in the package directory and typing pip install --upgrade dot. You'll see that it uninstalls the package and then reinstalls it. That's it. Have fun with this exercise. It really reinforces everything you've been practicing throughout this lesson.
As we discussed earlier, autoregressive models are used to study systems which evolve over time. They assume that some future events depend on what happens in the past. In the context of applying autoregressive models to music creation in AWS DeepComposer, we think about time a little bit differently, more like an edit history, which means that when you use AWS DeepComposer to compose music, it makes the small changes iteratively over time so that the melody sounds more and more similar to the dataset that the model training is performed on. During each change, chords can be modified, embellishments can be added, and sections can be added or removed. We call this model autoregressive not only because we represent time in our inputs, but also because the output is generated iteratively over time. In this section, you will learn about the ARCNN model in the context of AWS DeepComposer and music. Here is a high-level summary of how ARCNN model works. Imagine you create a simple input track containing 4 notes. During inference, the ARCNN model iteratively updates your input track to sound more like the training dataset. We refer to these as an edit events. So what are edit events? An edit event is when a note is either added or removed from your input track during inference. In the AWS DeepComposer Music Studio, you can set the maximum number of notes to be added or removed. Let's look at an example. Imagine that inference occurs in discrete cycles. During the first cycle of inference, the ARCNN model adds a new note shown as an orange box. We refer to that as a single edit event. Cool, so we have completed our first cycle. What happens next? Immediately, we want to update our loss function. Remember, our goal is that the edit event move your input track to a state where it sounds more like the music it was trained on. As we learned before, a loss function is simply a tool used by the model during training to compare and then try to minimize the distance between the predicted value and the actual value. Based on this check, the model creates another edit event in an attempt to minimize the loss function, or said another way, continue to make your input track sound more like the dataset it was trained on. So here in cycle 3, we continue this pattern of edit events. Let us now hear some output samples produced by ARCNN algorithm. In the first example, the model has learned to remove out of tune notes and add missing notes to make the melody sound better. Let's listen to the input melody. Now let's listen to the corrected melody. In the second example, melody has been converted to resemble the training dataset, which is Bach music. Let's first listen to the input melody. Now let's listen to the output melody that resembles the Bach music. You're now in AWS DeepComposer Music Studio. Although AWS DeepComposer has been designed for educational purposes, some of our customers have found the generated composition source of inspiration for creating more music. It is the piece where the collaboration between AI and human creativity happens. In this list here, called Your Composition, you can find all the compositions you have previously created. You can choose to load them and work on them further, or for the purpose of this demo, I want to start something from scratch, so I'm going to choose to start composing. That takes me to the next step, which is input track. Before I input track, let me rename this to Udacity Champions, because hopefully this music we are creating together is going to cheer you up in your learning journey. You have 4 options to input track. You can either know how to play piano, so you can connect your AWS DeepComposer keyboard and start playing, or there is a virtual keyboard here. You can also use your laptop keyboard to play piano, as you see A, W, S, D, F, G. To do that, you choose record, you start playing, and the melody appears here. If you're like me, not very good in playing piano, you also have 2 options. You can either import a track, which needs to be a MIDI file, or you can choose one of the sample melodies we have provided for you. I like New World, so I'm going to choose this one. Let's listen. Once you like your input track, choose Continue to take you to the next step. Next step is ML technique. We have ARCNN, GANs, and transformers. ARCNN makes your music sound more like Bach music. GANs add accompaniments to your track, and transformers extend your input track by up to 20 seconds. For this exercise, I'm going to pick ARCNN. As we learned in ARCNN method, notes are automatically added or removed from your input track based on the parameters. So let's go and see what parameters do we have here. The first one is maximum input notes to remove, which controls the percentage of input melody to be removed during inference. By increasing this parameter, you are allowing the model to use less of the input melody as a reference during inference. So I'm going to lower this one to 70. The next one is maximum notes to add, which controls the number of notes that can be added to the input melody. By increasing this number, you might introduce notes which sound out of place into your melody. I'm going to lower this one to 90. The next one is sampling iteration. Sampling iteration controls the number of times your input melody is passed through the model. Increasing the number of iterations results in more notes being added and removed from the melody. I'm going to lower this one to 90. The next one is creative risk. Creative risk controls how much the model can deviate from the music that it was trained on. More technically, when you change this value, you're changing the shape of the output probability distribution. If you set this value too low, the model will choose only high probability notes. If you set this value too high, the model will more likely choose lower probability notes. So I'm going to pick maybe 0.8 for this one. Once I'm done, I'm going to choose Continue.
Let's go on a tour of the scikit-learn source code. This is really why I wanted you to learn object-oriented programming and how to make a Python package. If you want to understand what packages like pandas, scipy, numpy, or scikit-learn are doing, you need to understand at least the basics of object-oriented programming. As we go through the scikit-learn source code, you'll see some things that are familiar based on what you've done in this lesson, including import statements, classes, and inheritance. You'll also notice syntax that we didn't cover, such as the @symbol, mixins, and cases of multiple inheritance, where a class inherits from 2 or more parent classes. Object-oriented programming is a big topic, and Python has a lot more functionality than what you've seen so far. I'm going to open Google and search for scikit-learn source code. It turns out that the code is hosted on GitHub. Here's the repository. Let's go into the sklearn folder and see what we can find. Okay, I see the linear model folder, which I'm guessing holds code for things like linear regression. At the very top is a tests folder. You can see that writing test code is an important part of developing a Python package, or really any program. Opening up the test folder, you can explore all the different tests that have been written for different functionality. Let's go back up to the linear model folder. Since there's an init file, you know that linear model is actually a package. Opening that file, this code should be somewhat familiar. The init file is importing the classes contained in each of the package modules. This is equivalent to the init file in your distributions package, where you were creating shortcuts to the class names. I'm going to go back. Now I'll open base.py and see what's inside. It starts off with a few comments, and then there are a lot of import statements. So the base.py file is using a lot of other Python modules or packages. Next, there's a variable called sparse intercept delay and a function called makeDataset. As I mentioned in the beginning of the lesson, a Python module can contain any combination of variables, functions, or classes. Scrolling down, this is where things get a little more advanced. The @symbol is called a decorator, and you might not have seen this before. I'll put a resource below the video if you want to learn about decorators. I'm going to scroll down a bit more. Here we are with the first class in the module. It's called linear model, and the class inherits from 2 parent classes, ABC Meta and Base Estimator. Then you can see the linear model class has a few methods. The dash before the decision function is just a convention that usually indicates that the function is only meant to be used internally inside the class and not by an instantiated object. If you want to get involved with contributing to a library like this, check out the issues page. It's at the top of a GitHub page. Here's issues. I'm going to click on it. You can read about the issues and see if there's something that you could contribute to. I'll also put a few links below giving guidelines about how to contribute to a GitHub project. Scikit-learn is a large package with a lot of code. But don't get too overwhelmed. Realize that a package like this was built over time with various people contributing to different parts. But the basic package you coded in this lesson is essentially how a much larger package works. You start small with just a few modules, and over time you add more and more functionality. PyPy, also known as the Python Package Index, is a repository where Python packages are stored. When you pip install a package, you are downloading and installing files from PyPy. Anyone can upload a package to PyPy. I'm going to show you the basics of how to do it. The PyPy website actually has a test repository as well as the regular repository. This is the test repository website. I'd suggest first uploading your package to the test repository to make sure everything works as expected. Then you can upload the package to the regular repository on this website. Remember that anybody can download and install your package if it's in the regular repository. The first step is to create an account on PyPy and the test PyPy repositories. If you go to each website, you can click on Register and make an account. I've already done this, so I'm going to skip this step. Next, go to your terminal and enter the directory with your package files. Let's open this DSND probability folder where the package is located. You'll see that there are a few extra files than what was originally in the package you were working with before. You'll need to add these extra files. The first one is a file called license.txt. Opening that file, this is where you put copyright information. I've used the language for the MIT license, which I copied and pasted from the opensource.org website. Next, you'll also need to add a readme.md file. I haven't filled out this file with enough detail yet, but this is where you would document how your package works. And finally, create a file called setup.cfg. All you need to put in here is some data about the name of your README file. Let's go back up one level and open the setup.py file. You can see I've named my package dsnd_probability. The folder with all the package files is also called dsnd_probability. If you want to upload this code to PyPy, you'll need to come up with a different name. Every package on PyPy needs a unique name. In the setup.py file, in the packages variable, use the same name that you put in the name variable. I'm keeping zip_safe to false because it means that the package can't be run directly from a zip file. This is especially important if your packages rely on data files that need to remain unzipped for use. Again, note as well that I've changed the name of the package folder to match dsnd_probability. I'm going to do a bit of hand waving here, though if you want to read more about how to upload to PyPy, I'll include a link to the documentation. Go to your terminal window and make sure that within terminal, you're inside the folder with your package files. Then type python setup.py sdist. If you look at the package folder, there are now a couple of new folders that appeared. Inside the dist folder is a tar.gz file that you're going to end up uploading to the PyPy repository. Next, go back to the terminal and install the twine package with pip install twine. And then type the following command to upload the package to the PyPy test repository. It's twine upload --repository -url, then https://test.pypy.org/legacy/space/dist/*. This is what it looks like. Hit enter. It asks for my username. This is the username for the test PyPy repository and my password. Okay, so it's giving me an error that says I'm using the same version that I uploaded before. So I'm just going to change this from 1.2 to say 1.3. You might end up having this error as well and having to do the same thing. This is because I've already tried to upload this package before with the same version. So I'm going to go back and I'm going to delete this dist folder and this extra info folder that were created before. And now I'm going to repeat the same steps. Python setup.py sdist. Okay, now I'm going to try again. Twine upload --repository -url. Enter my username, my password. Okay, and this time it looks like it worked. So I'm going to go to the test PyPy website for a second. I'm going to log into my account. And okay, it looks like everything uploaded correctly. Let's go back to terminal for a second. I can now actually pip install this package using the following command. Pip install --index -url https://test.pypy.org/simple/space dsnd-probability. And this says to pip install the package from the test repository website. Okay, it looks like it installed successfully. Assuming that everything goes well and you're ready to upload the package to the regular PyPy repository, here's how you can do that. Type twine upload space dist/star. Enter your username, your password. Okay, and now let's check on the regular PyPy repository website if everything uploaded. I'm going to log in. And okay, it looks like everything uploaded here as well. So remember, we already installed the package from the test website, so I'm going to uninstall it. Since the package is now also on the regular repository, I can pip install directly. I just write pip install and then the name of the package. Okay, and it looks like everything installed correctly. Now I'm going to see if I can use it in a Python program. I'm going to open a new terminal window, and I'm going to open a Python interpreter. And now I'm going to say from dsnd underscore probability import Gaussian and import binomial. Okay, so far so good. So if I say Gaussian 10, 7, hit enter, then it's made a Gaussian object with mean 10 and standard deviation 7. If I type binomial 0.4, 25, hit enter, it gives me the mean, standard deviation, probability, and number of samples. So it looks like it worked. So what I've shown you is the very basics for getting something up and running with PyPy. If you're going to upload the package made in this lesson, make sure you use a different package name than dsnd underscore probability. Otherwise, you won't be able to upload the package because the name will conflict with the package I just uploaded. Also realize that in the package name, I used underscore, but if you go back to the PyPy website, the package gets named with a dash, so that's something to be aware of as well. When you're pip installing, you'll have to use the dash, but then when you're using it in the Python interpreter or in your program, you'd use the underscore. So now it's your turn. Follow the instructions in this video and try uploading your own package to PyPy.
This is the output melody. Let's listen to it. Alright, I want to edit melody a little bit. In this step, as you see here, I can just drag some notes out of the picture so they are removed. Or I can introduce more. I can extend them, or I can move them, or I can decide to extend some of the notes we previously created here. I can always play, try again, and continue these steps. Once I'm happy with this melody, I'm going to click on Apply Changes. The created composition might not be my favorite, so I can go back to this step, change hyperparameters, and enhance again. Let's listen to this one. Alright, I want to edit this melody again. I'm removing these. Choose Apply Changes. Once you are happy with the composition, like me, I'm going to rename this one to my favorite. You can choose to download melody. You can export your melody to a digital audio workstation like GarageBand and further indulge your creativity. Or again, if you want, you can enhance again. I think I'm done with creating this music, so I'm going to choose Continue. Congratulations! You have created your very own piece of music. you have a couple next steps you can take. For example, the one I want to do right now is adding accompaniments to my track. You can generate accompaniment track using GAN technique. So let's choose Generate Accompaniment Tracks. You can choose Generative Algorithm. I'm gonna pick MuseGAN. And I like rock. So let's go with that. You can choose Continue. And you have accompaniments added to your composition. You can choose to play, and in each step, you can decide to mute and unmute any of these tracks you like or dislike. Alright, hope you enjoyed your journey. So next step, what you can do, you can decide to share your composition. And that's where you can participate in AWS DeepComposer Chartbusters Challenge as well. You choose Share Composition. In this step, you might need to sign up or sign into your SoundCloud. You can rename your track. You can add description, which is optional. And you can choose the competition you want to participate in. We have Melody Harvest, we have Melody Go Round. You can choose a View Chartbuster Challenge to learn more. Melody Harvest, you need to train your own model. For Melody Go Round, you just need to compose music. So if you just composed a music, this is the competition you need to participate. So choose Melody Go Round and share on SoundCloud. And we automatically submit your composition for consideration in AWS DeepComposer Chartbuster Challenge. Good luck!
Hope you enjoyed this course so far. In this section, you learned about generative AI and its applications. You got hands-on with AWS DeepComposer and experimented with the most popular generative AI techniques. You briefly learned how those models work in the context of music and AWS DeepComposer. Now I invite you to put your knowledge into work and compete in AWS DeepComposer Chartbusters competitions. You have the chance of winning prizes and glory, including a ticket to AWS annual conference, AWS reInvent. To learn more, check out the instruction in this section. Happy composing and competing!
This has been quite a journey. You started out learning the basics of object-oriented programming, and you ended up with a Python package that you can share with the world. Let's review all the concepts from this lesson. First, you wrote some basic object-oriented programs using clothing. You coded a few classes and instantiated objects. These objects had a set of characteristics called attributes and a set of actions called methods. Then you started working with a more complex class representing Gaussian distributions. You practiced writing magic methods and writing programs that included inheritance. Next, you converted the Gaussian class into a Python package, and then you added another class called binomial. Once all of this code was ready, you uploaded this package to PyPy. That's a lot of work for one lesson. You should be really proud because, as I said in the beginning, I don't think too many people know how to write a Python package and upload it to PyPy.
You have come a long way. Congrats for finishing the machine learning with AWS lesson. In this lesson, you learned about AWS machine learning offerings. You then turned the engine and went through reinforcement learning fundamentals with AWS DeepRacer. At the end, you have learned generative AI with AWS DeepComposer. Hope you enjoyed this lesson.